a long way there. So, all right, we can start. Cool. Well, welcome everyone. It sounds like we're live, so that's exciting. So we're here today to talk about teaching and learning compilers using this incremental approach that we've been working on at Indiana University for quite a while. And now we finally have a textbook to go with it. And so I'm trying to get the message out to everyone around the world about sort of this new style of teaching an introduction to compilers, right? This is not an advanced compiler course. It's like if you've never seen compilers before, this is the course for you. It helps to have been in a some kind of programming languages course ahead of this, so you're not seeing abstract syntax trees for the first time. Hopefully, that for students, it's a review of that kind of stuff. Okay, so what I'm going to do is I'm going to start out with just sort of like an overview of the approach. This is the kind of stuff that I'll teach in the first week or so of the class. And then depending on what the audience would like to do, I can either kind of describe what the students do in the first 2 weeks, or we could even try to whip out Emacs and try to code up some of what the students do in those first 2 weeks. So depending on how interactive you all want to make it. Okay, so, right, so you're all familiar with this, well, maybe some of you are familiar with this pipeline layout for how a compiler is structured internally, right? So this is the standard thing you'll all see. We've got some source language, you parse it into an abstract syntax tree. You've got the front end of your compiler that brings you into an intermediate language. You maybe have several intermediate languages. You do stages of lowering, and you get to a final target language like x86. And we call each of these arrows a pass. And one of the things that we've been doing in Indiana for a long time, and this goes back to like Dan Friedman and Kent Divig, is that they would use this nanopass approach, where for pedagogical reasons, you try to slice up these passes into fairly small chunks. Each have a very focused responsibility, okay? So that they're sort of easy to bite off. And also you can, after each one of these passes, you can test, right? You can run the interpreter on the output. We've got interpreters for all the intermediate languages, and you can check to see if your program still behaves the way it's supposed to. Okay, so part of the way we do compilers, this course, part of it is using the nanopass approach, but that's not all. Okay, that's just one aspect of it.
Do you want to take questions as we go?
Absolutely.
So one of the things that I feel that diagrams like this never quite accommodate is that we often got static analyses that we do as you go along. And then there's a question about, do you do an analysis, immediately do a transformation, or do you somehow maintain analysis information, static information through successive passes? That's a bit hidden in a diagram like this.
Yes.
And the nanopass story doesn't really answer that question.
No, that's orthogonal. And I've
exactly orthogonal, but
well, I've struggled with this issue too. And over the years, we've tried out different approaches. One of the things that we do is we will often stash extra metadata on the AST in various places and squirrel it away.
Then every transformation has to maintain the metadata.
But then, right, and so we don't always do that.
That's quite a big tax sometimes
Yeah.
on a nanopass.
Right, so we usually don't keep it around very long. We usually consume it on the very next pass.
Consume it, yeah.
Make it consume it, and then if it's the kind of thing where maybe we need it again much later on, we then recreate. Oftentimes we'll recreate it. So we might do a type checking pass. Like if we need something about types, we might do another type checking pass later on.
Yeah, it's always bear in mind. Yes,
Yeah.
this picture.
Yeah. Okay. So, but the other aspect of the way we structure the course is that it's incremental. And I think this is the sort of crucial point. So what I've got a picture of is these are the input languages to the compiler. Okay. So the very first input language to the compiler is tiny. It's integer arithmetic plus variables, local variables, and that's it. Okay. And the students compile that little language down to x86 in the first 2 weeks. Okay. And it's a very simple compiler. It doesn't need very many passes. But we go all the way down to x86. Okay. And then what happens in every sort of subsequent 2 weeks, we add new language features to our input language. And then we sort of have to then change the compiler, either adding new passes, maybe adding more cases to handle new AST forms in existing passes. Okay. So we add Booleans and conditionals in sort of this next phase. And we add while loops. And we add tuples and the need for garbage collection, and then functions. And there's actually a few more layers out here, lambdas, Mexican scope functions, and so on. And so the cool thing is you've got right off the bat in those first 2 weeks, you've got a working compiler. The students can start running on making a test suite, and then with each extension of the language, they keep their old tests, but then add new tests, and they can be doing the regression testing the whole way through. And they can get that positive feedback of, oh, cool, I've got a working compiler, and then they keep getting back to that point of having the working compiler as we go along. So one of the other benefits I think of this approach is that you get to see why certain passes are in the compiler, or why your IR has to be a certain way, because the language feature that sort of necessitates it, that's when you add it to the compiler. Okay, so for example, we start doing data flow analysis when we introduce while loops. Before that, we don't need it. Okay, and you introduce garbage collection, we get tuples. So that's that big idea. So this is a diagram of the whole book in the chapters, okay, and there's some variation of what you can do, what you can include. So here you see, okay, this is the arithmetic and variables. We do not do register allocation right away in that in chapter 2. And the reason is that would be too big to bite off in 2 weeks. So instead, in this project, we compile all the variables, we assign them to stack locations as if we're spilling everything. Okay, because you need to learn how to spill anyways. And so we learn about putting variables on the stack here, and then we do register allocation in chapter 3. And we use a approach. We of course do graph coloring, but we do graph coloring inspired by Sudoku, just as a more fun way to do it. Okay, so there's this what's called saturation-based graph coloring, which corresponds to using pencil marks in your Sudoku game. And so that's what we do there, which is a lot of fun. Right, conditionals. Tuples, there's sort of this, you can play around with what order you do certain things in. If you want to do efficient tail calls, then you have to do the way we do it. You have to do tuples first. You definitely need tuples if you're going to do closures, because we compile to flat closures, what they're called, which is the way Chasing does it. If you want, all of these languages up here are statically typed languages. If you want to cover dynamically typed languages, then that's chapter 9. And there you learn how to do sort of a Lisp style, 64-bit tag pointer thing. And then kind of unique to this book is my background in gradual typing. Of course, there's a chapter on how to do gradual typing. But then kind of an interesting thing, I also have a background in generics. And so it turns out it's easy to leverage the infrastructure for gradual typing to do a sort of a generics that does auto boxing at the boundary between polymorphic and monomorphic code. So that's what that is. I normally don't get, in a semester, we can usually barely get to Lambda. Okay. And then we try to do like final projects. They can sort of pick from down here on final projects. And I should say the loops was sort of a fairly new addition to the course. This is the sort of our excuse to do data flow analysis. Prior versions of the Indiana course, like on Kent did, they taught it just didn't have that. because it was more functionally oriented.
Is that the same chapter 5, recursion?
Well, so
Or does recursion show up somewhere else?
So with recursion, I mean, in some sense, you don't, because of that function call boundary, you sort of don't have to do data flow analysis. Right.
You're saying that loops are harder than functions?
A little bit, yeah.
Oh, interesting.
Yeah.
Okay, well, let's just do recursion.
Yeah, that's fine. You can see this is sort of like a dead end over here
Yeah.
that you could,
So you're saying just don't do this?
you could
That's weird.
get chapter 5 and everything.
I'm a bit surprised.
Yeah.
I would have thought that all the problems would be the same. If we're saying that.
Well, it's because I mean, this is, it's all about, in here, it's all about liveness analysis and register allocation. And when because what's happened is you do register allocation on a per function basis, or a function call basis. And so when you've got that tail call in there, you're going to a different world in terms of where the local variables live.
I see. So you're saying that maybe you're saying that if you're doing tail calls, then at the tail call, you follow a calling convention.
That's right.
So then you're going to get worse codes than if you've done some very clever wood-whammy register allocation.
Yes. And
That would be a good thing to exemplify, to show here is a program, which if you write it recursively, you get worse, slower code. Yeah. Than if you program the loop explicitly.
right. And so here you get cycles in your control flow graphs, and that's why you have to do the data flow. But over here, if you're just doing your recursive functions, then you don't.
You don't have to do that, though. You could just establish a calling convention at the top of the loop as if it
That's true. You could. You could.
It's just that if you do it with recursive functions, you're kind of forced to. You're not even forced to. You could have a custom calling convention, right?
Yes.
You can play it both ways.
Yes.
Yeah.
Lots of fun variations. All right, so just a little bit about some of how I do the logistics of the course in terms of how I teach it. Of course, we want to have a way for students to ask questions on, we use Slack, other Discord and things like that are great. They can answer each other's questions, and whatnot. Each chapter basically is in a description, and we try to do one chapter every 2 weeks approximately. I encourage the students to do groups of 2 to 4 students, sort of the typical grouping that we do. And most chapters have these challenge problems. So if you're teaching for like a grad course, then you might assign some of those challenge problems to sort of beef up what's being asked. And then the other neat thing is that we use what we call an auto grader. So the students submit their code, and then we run their code on a suite of test programs that we've developed. And then, so we can, their grade will depend on how many of those test programs they get right. Okay, and so this allows us to sort of raise the bar in terms of how correct our compiler needs to be, because it's not just, a teaching assistant sort of looking at their code being like, oh, does this sort of look right? Instead, it's like, oh no, we're testing it in a whole bunch of test programs, catching along with bugs. So that's that. Of course, the students. Actually, I'm guessing is everyone in the audience pretty familiar with like concrete syntax, abstract syntax? Yeah. Okay. So I'm gonna skip over. We use grammars an awful lot in this course in terms of thinking about how they're going to write the code and what languages they're working on. So it's a very sort of language driven course. So they spend a lot of time looking at grammars. Even I'm going to flip ahead, even grammars for abstract syntax. So maybe this is slightly unusual to do, but we've got, so like here, we're using racket structs to represent our AST nodes. And these are like the constructors that you would be using for your racket structs. And we like to specify our languages in terms of those. And then on the Python side, of course, these are constructors for Python objects. And on the Python side, we use the standard Python AST module for especially starting out the first layer of our source languages and then somewhat into the intermediate languages. Okay, so we can use the standard parser from Python and stuff like that. And there's a bit of a trade-off there. So for example, like I'd much prefer to have just one AST node for primitive operators, but the standard Python AST has like a separate AST node for binary operators and numeric operators. So, oh well. But we just like to stick with the more standard thing, right? And so like here's some of the the standard Python classes for representing abstract syntax. And if you're not used to seeing type annotations in Python code, this is sort of Python 3, sort of a new thing. And they've got these things called data classes that look out to do this. We're defining this. And it's already been applied to the standard classes. And then right, and then here's like our struct definitions. And so this is all, pretty standard approaches to representing our programs with abstract syntax. One of the things we try to do is we don't want to ask students to get too fancy in terms of their programming, like the number of different language features in their code. Like we try to keep that to a fairly minimal set of things. And so like in the next couple of slides, I'm just going to kind of go over like what features of like Python or Racket do we use over and over again in the compiler. Okay. And so pattern matching, thankfully was added to Python in version 3.10 last year. And so that's like, wow, that's huge. So we use pattern matching all over the place. So here's, typical, this is a typical recursive function over an abstract syntax. Where here we're just computing the height of an AST. And, we just start off by saying, okay, match on your expression. And then you've got, a case for each, item in the grammar, right? And so this is very much following the, if you're familiar with like Matthias Weiss's textbook about, what's the name of that? I'm blanking on the name of that textbook. Oh gosh. Anyways, the one it's the idea of like, okay, you write your code driven by the grammar. So there's 5 different options in the grammar. So you have 5 different cases, and then you can write out a pattern for each. Okay. You got your recursive calls there. So we just do that sort of over and over again, encouraging, whether that's in Python or in Racket. It's nice that in Racket it's almost syntactically the same. Let's even call it match the same. So that's nice. The way I communicate the semantics to the students, right? Their compilers are supposed to be implementing these languages. Well, what language exactly are they supposed to be implementing? We communicate that via definitional interpreters. Okay, so we just write these very simple recursive functions for the interpreters. These are spelled out in the book, and they need to match the same behavior as these interpreters. Okay, now there are subtle ways in which these interpreters are maybe more restrictive than the real Python language. For example, we say things like the integer arithmetic is actually restricted to 64. What can make sense for 64-bit integers? Okay, and we don't get into the, how would you implement big integers or anything like that. That's really kind of a thought on the issue that we don't do. And so what we tell the students, so like for example in Racket here Racket has a nice fixed num. You can specifically use fixed nums, and then you'll get errors if it goes out of that range. And so what we tell the students is any program that can run through to completion on these interpreters, those programs you have to match the behavior for. For programs that would produce errors in one form or another, whether that's we do have type checkers, or produce an error in the interpreter, then we tell students they don't need to match the behavior, like that they don't care about those programs. And we are dodging a big chunk of what a production quality compiler will need to do by saying that, because production quality compiler oftentimes some of these error cases need to be defined errors, and we're not doing that. And that's very much in the interest of sort of like time and what you have, how much to bite off. Right. So that's what we use those interpreters for. Okay, so now here we come to our first language, both the Racket version and the Python version. And so as I mentioned before, it's integer arithmetic, so we have literals, negation, addition. Actually, I think we also have subtraction. Didn't bring that in. We have input from the user. Okay, that's actually kind of an important thing to have in the language. If you don't have input like that in your little language, then you get clever students who decide to implement a compiler by interpreting the whole darn thing at compile time and then just spitting out the number, move 42 to REX rec and then do a rec Q. So that's why that's there instead. So they actually have to write a compiler. It also is a side effect. So learning how to deal with side effects is an important thing. And so that sort of triggers that aspect of it. And then here's the part of the language that's variables. So you have let binding and then use of variables. That's on the Racket side. On the Python side, instead of let binding, we'll just have assignment statements. Okay. And then a print so you can get a observable output.
So is this just the different? Are you like doing a different language? Is the source language that you're compiling from different in the two different versions of
Yes. So this is the one for Racket. This is the one for Python. I was sort of forced to make it slightly different. And these are like as close as I could get them, while staying, strictly within Racket versus strictly within Python. Like Python doesn't have a let.
So like they did it like they're both writing a compiler in Python and the language they're compiling is like a baby Python?
Yes.
I see. Okay.
And then the same story for Racket. Thank you for that question. That's an important point. Obviously, these are orthogonal choices, but we've sort of always had a tradition of doing it in the same, having the baby of the whatever language you're using. Okay, so this is the starting point for our first 2-week project. And then we just love to, go over some example programs and sort of talk about maybe already there's a little bit of trickiness going on. So for example, in Racket, you already have to deal with like name shadowing as a thing. And then you can think about like, well, what is that? How is the compiler going to deal with that? And then on the Python side, there isn't any name shadowing, it turns out, in this little language. And this is just 2 assignments to the same X. So actually that makes the Python version is a little bit easier in that sense. Right. And then it's like, all right, now that's our input language. Where's our target? Our target is x86. And we're going all the way to x86. And so some of the students have had a little bit of assembly, but some of them haven't. So we kind of need to do a quick kind of review or intro to what it looks to, what a laptop or your desktop is doing when it's running assembly code. And so we introduce sort of a simple mental model of what's going on in the computer, where you've got your registers, you've got your program counter, you've got your memory with the heap, your program, and your procedure call stack. And they kind of need to know about even though we don't have user-defined functions right off the bat, they do need to know about the call stack right away because we're going to put local variables. We're going to put variables on the call stack. All right, so then here's this tiny subset of x86 that we use right off the bat, and then we add on to it more instructions as we go. And so it is kind of a slightly funky, instruction set. All these 2 argument operations that do in place updates, which is kind of depending on how you look at it, weird. But on the main reason why I chose to do x86 is that it's just real. It's like, the student, that's what's running on the student's laptop. There's something to be said for for, not having to have emulators or anything like that. It's the real thing.
What do you do now that like people are walking with M1s?
So thankfully, for example, mine is one of those M1s. Thankfully, they still run x86. You just there's some flags that you have to give to your GCC to tell it to generate the right style of code. It just works. I'm a little worried that it might stop working sometime in the future. I might have to do an add-on to the book of how do you compile to ARM. I mean, that would be actually a nice thing to have eventually. So maybe if any of you maybe have not seen, well, how many of you have seen x86 before? Okay, everybody. Okay, great. So you're familiar with okay, this is like your dereferencing pointer basically with this syntax. And you're reading you're getting addresses in a register, offsetting it, and then reading from memory. Okay, and here's like a tiny little x86 program where you're okay, you're putting 10 in the RAX register, and you're adding 32 to that register, and then returning from your function. And of course, the calling convention says that the return value goes on. All right, so that's sort of kind of the overview here. And then the next thing that I typically do with the students is we kind of brainstorm about what's the difference between this LVAR input language and x86, right? Because the job of the compiler is going to be to sort of bridge those differences. So we just try to brainstorm that. And then we then sort of categorize all those differences and then try to assign compiler passes to handling those differences. Okay. And I kind of steer people into a certain sort of organization and give some rationale for that. And then here's sort of the passes that I typically suggest that the students use and implement. And then I kind of go into the details of that. And so that first 2 weeks in is then they're implementing all of these passes for this little element. So maybe, and I guess one question I have for y'all, we could go ahead and do this sort of brainstorming session, and then we could either be just sort of walking through how I do these, or we could do sort of an interactive thing where we can live code one of these passes and see what, I'm kind of curious as to how many of you would just sort of like to see me sort of describe all these passes. So, and then let's do a vote for that versus interactive coding. Is it clear what I'm asking them?
So the describing all might be quite quick, and that would get us to some of the more advanced features more quickly, right? So, well, maybe you just want to concentrate on the pedagogy, in which case we could go as slow as it needs.
Yeah, I mean, I'm not.
I'm finding interested.
So the last time I did this tutorial PLDI, just getting through all of this was what we had time for.
Right. Well, I'm interested in how do you introduce closures? So data flow analysis and loops.
Yes. So we're
pedagogical point.
Yeah. So I don't have much prepared sort of for that later stuff. So
you've done it, and
yeah.
But
I can. I'm happy to
ad lib
on that stuff for sure. So
other people may.
I guess to what degree is the structure you're describing here laid out in the book? You're describing a kind of open and interactive process of talking to people, trying to figure things out, but also you have a book which is
yes.
Stubbornly unmoving pages.
Absolutely. So yeah, so I mean, after this brainstorming session, I then sort of try to steer people into this sort of structure. And part of it's because students can be really creative, but they can also get themselves into a lot of hot water by being sort of overly creative. Now, that being said, what's the trade-off? So what I tell the students is I give you interpreters for all the intermediate languages that these passes go through. If they want to do something different, then they may end up with an IR that I don't have an interpreter for, and then that's on them. Okay,
got it.
so yeah, that's the. So if there's a choose your own adventure, but they realize if they go too far off the path, then it gets harder. I've kind of played around with how prescriptive to be over the years, and I found that I had to lean a bit more toward the prescriptive side to keep people on track. Okay, so oftentimes, so we just start staring at these input programs versus output program and start brainstorming. Well, what's the difference between x86 bracket? And I probably should have had a slightly more complicated input program, right? So you could imagine bigger expressions, lots of sub-expressions.
With like explicitness about locations. Like one.
Yeah. Right. So here it's like, oh, you've got very specific names for a finite number of locations, like the registers, and then memory addresses are all very unique. Right. Whereas like on the racket side, you've got let bindings, but you could be using the same name in multiple different let bindings, right? So that's non-unique. So you have to deal with that difference. Super obvious differences.
One's declarative,
One's declarative versus imperative. So that's a really broad characterization that could mean lots of different things to different people. So maybe could you pick out some very specific thing that jives with what you're trying to say?
Well, I mean, for the rocket, I'm most focused on the mathematical side, I guess. But if I look at assembly code, I'm more focused on the operation I did on the.
So maybe one aspect of what you're talking about is that like when you do one of these binary operators, the result is sort of this temporary thing that then flows into the surrounding expression, right? Whereas in x86, your result is always going into a register or into a memory location. And I think that's one concrete sort of difference behind what you're talking about. You want to sign your hand up?
Yeah, you have like control flow, sending, maybe like zero.
The control flow here is super explicit, right? Either it's very sequential or you've got like explicit jumps to labels, things like that, right? Whereas over here, like maybe imagine you've got some giant AST, some big nested lets and things, and the control flow is really like, it's not really explicit in the syntax, but you know that it's like, oh, there's like a depth first left to right traversal of the AST is, it turns out for both Racket and Python, that's the order of evaluation with, of course, different caveats for certain language features like if, like short circuiting operation. So yeah, so control flow, dealing with control flows and the different ways that these languages work with control flows is a big thing that needs to be in the compiler. All right, so this is like oftentimes the brainstorming, this is sort of the list that we end up coming up with. I think we've pretty much covered all of these things just now. All right, so then what we try to do then is groups those differences into sort of passes that are responsible for each of those differences. And this is a little bit where like the nano pass aspect comes into play, is that we're trying to split them up into a fair number of passes that are each manageable. Something that about the way I do the nano pass is I try to make sure that each pass has sort of like a meaningful sort of realm of responsibility, and I watch out for sort of things that might feel ad hoc or things like that. So this is sort of the passes that I like to have for this thing. So for example, making sure that all your going from variables that are not necessarily unique to a setup where all your variables have unique names. That's just this uniquify pass. This assign homes pass. That's job is to replace variables, of which there sort of could be an unbounded number of variables, replacing those with with locations on the procedure call stack. That's what we do in assign homes. And then of course, later on that pass gets enhanced to deal with register allocation. And then then there's of course, going from sort of thinking about operations like plus that produce temporary results to these instructions like add to that like operate on 2 arguments and one of them is in place. That's the job of select instructions to handle. And then separately, we have this patch called remove complex operands, or in the old days we called it opera star. It's like a kind of a joke with a cleaning star. But the idea there is that when you've got like a plus operator with sub-expressions, once you get to x86, it's going to be an add queue, and those sub-expressions better just be like atomic things like a variable reference or register or an immediate constant kinds of things. So they have to be these atomic things. It can't be some big area sub-expression. So we introduce temporary variables for all those sub-expressions. That's what that pass is all about. And then this explicate control, this is all about handling the control flow that you talked about, of going from, sort of this AST traversal kind of control flow to having it be explicit in the syntax. And this chapter of the book actually cites some of Simon Peyton Jones's old papers about optimizing conditionals. So it's so fun to have you in the audience.
We can do that, compiling the continuations.
So this pass has continuations in the form of code, like you're passing. It's like a continuation passing thing, but the continuation is a chunk of code.
I was reading the paper, compiling without.
Compiling without.
Which is a bit more recent.
Okay.
And much better
Okay.
than those old guys.
Yeah.
Don't ignore them. They were wrong-headed.
Yeah. I mean, I followed what Divvig was doing. So he never did CPS.
No, I don't do CPS.
Yeah.
That's why it's called compiling without.
Yes. Yeah. So I think this probably sort of it would probably be like, oh, yeah, when you look at it. So, okay. So then there's a question of like what order to do the passes in. And for the most part, this is straightforward. Like there's some obvious things you want to do in a certain order. Like right. So, for example, remove complex operands introduces a lot of temporary variables. And then, down here, assign homes gets rid of all those variables. And I mean, if you were to try to do like that first, and then do remove complex, then you'd all of a sudden have a whole bunch more variables to deal with. And you'd have to do assign homes again. So that's like, obviously that would not make sense. So sometimes there's definite reasons to do one thing in front of the other. Though there's some places where it's more tricky. So for example, here I've got select instruction followed by assign homes. But there's really almost like a circular dependency if you want to do sort of the optimal job of selecting instructions and assigning homes. And that's why, like in Shay's scheme, they actually iterate these 2 phases. And we did that in earlier versions of this course, but that's really hard to debug. And students struggle with it. So what I'm sort of suggesting these days is to do it in this order. And then what happens is after doing the assigning homes, you still sometimes end up with instructions where, for example, you have like an add queue where both operands are like stack locations. And that's not allowed in x86. And so then we do this patching up where we have to split that into 2 instructions and use an extra register to sort of fix things up. And so we sort of pay a little bit of price in terms of code quality to keep things sort of linear here and simpler for the students. Whereas like the original sort of shade student thing doesn't need the special patch instructions.
I'm curious, do you use the same data type of x86 or you trying to be more explicit in terms of the data? So, because you mentioned a case where you creating an illegal x86 singer. So do you still consider it a type of x86 or it's more like legal x86 and then you convert this illegal x86 and convert it to the
Yeah, so this is a great question about sort of like what kind of checking do you do on the intermediate, on the IRs?
Yeah.
And we have type checkers for like the LVAR level code, and we have something that we call our C level IR, because it's sort of slightly reminiscent of C in terms of its abstraction level. We have type checkers for those. We do not have a type checker at the x86 level at all. Now we do have these interpreters we have an interpreter. So this is actually an important point. So here after, like right up here after select instructions, we have, if you look at those programs, they're x86 code, but they still have variables. Yeah. And so you can't run those like on your computer yet, right, natively. And so we have an interpreter for that you could run instead. And then from here to here, okay, from here now you no longer have any variables, but you might not be following all the rules about x86 instructions. Okay, and we still use the same interpreter, and we don't have any special checking in our system, so the students just have to get that, they have to get it right. Okay, and then they'll really find out whether they got it right or not when they spit out the x86 code for real and send it to GCC. And part of this just has to do with how many cycles we have to maintaining all the interpreters and type checkers and things. There's a cost to that. So there's certain places where we've not gone as far as we could have gone in terms of the consistency checking and checking invariants that are necessary. I think that answers the question.
Yeah. I mean, so basically the type between different compiler paths is still going to be x86 data.
Yeah, we basically use the same. Well, one other thing to mention is, so we're implementing this in Racket and in Python, and those AST classes are dynamically typed, not statically typed, right? Now, like Andrew Tolmack has a version of this course where he did it in OCaml, and then you would have, and people have also done it in Haskell as well. And so if you're doing the course in one of those languages, then you would have statically typed IRs. And then there's obviously, even then there's a question of how statically typed you go. Like, are you going to make it dependently typed? Maybe you need it dependently typed in order to capture some of these invariants about like how many memory accesses you have per instruction. And you could go, further in that extreme. It's just a question of how early of checking can you get, and how much work you're willing to do.
Do you know that the university would be this course in OCaml?
Yeah. Right, that was Portland State University. And there is a GitHub repo for his OCaml code. That's Andrew Tolmack. Andrew Tolmack has been doing functional compiler stuff for decades. He's an expert in compilers. Okay. Let's see, where are we in terms of our initial? think we still have a half an hour. So at this point, we need to do the vote. Okay, so it'll be option A will be me sort of describe these passes. And option B will be, let's pull up an Emacs window and start coding. Okay. And also, I haven't been getting quite as many questions as I did at the PLEI tutorial, so definitely encourage you all to ask questions. We can take this as slow as we need to. But yeah, let's go ahead and do that though. So how many for I'll go through and describe all these passes. Okay, 0 for that, and then how many? Unanimous, all right. Let's bring the code out. All right. Well, so actually, let's I want to start here, which is that if you go to the the page for this tutorial, I've added a link there to a web page that I've created that sort of like points you to like where on GitHub you need to go to get the student sort of all the public code, student support code. Okay, so you can follow that link and then clone some stuff from GitHub and you'll have a good starting point. And the main things that you'll get. So hit this compiler.py. So this is the Python version, and this is the in the student, the Python student repository. This is a little template to help students get started. Okay, so there's this compiler class here in bracket, and then a bunch of methods. So for example, the remove complex operand pass gets kicked off here with this function. And then there's like select instructions and assign homes, patch, and then the very last thing is adding the prelude and conclusion of the point. All right, so this is sort of like a little bit of a skeleton for them to get started. And then I have sort of two files here to help sort of run the code and test it. And actually, I whipped up a new one just for use today, which I call simple test. So it's a bit of a harness for running these compiler passes and the interpreters, but it's just meant for this first sort of 2-week project, chapter 2, and then there's sort of a more full-fledged run test script that's much more complicated, but is set up with a lot more bells and whistles to handle all the languages that as you progress through the rest of the book. Okay, so the simple test here, what does it do? You create object from that compiler class that you're implementing, and then you decide which test programs you want to be running. Right now, I've got it set to just this one sub input test here. Let's look at, and this is a super tiny little.
Is it the same in the racket stuff?
So on the racket stuff, I do not have this sort of equivalent of simple testing. I just have the full feature run-test script that you could use. And that one has like different flags you can use to tell it like which tests. Like, do you want to run all the tests or just one test or things like that? So that one's takes a little bit more explaining to get up to speed on that. But okay, so what does this, what does this script do? It basically just uses, so and this is a little bit unusual, right, for a compiler class, is that we just read in the source code. And then call the parse function from the AST library, the standard one from Python, right? So normally you'd have like a third of your course dedicated to parsing. Here, we're just calling the AST module. So in the Python book, there is a chapter on parsing, right? And I basically teach them how to use a parser generator, Lark in particular, is the one that chapter teaches them how to use. But on the racket side, there's no such chapter. It's all just, it's S expressions, and there's not much to say about parsing S expressions. Anyway, so right off the bat, we don't do much on the way of parsing. And then, if you're just getting started here, then the very first step, just to make sure everything is working properly, is to just print out the program that you just read.
We mentioned that at one point, one difference between Python and rapid versions is that you can basically do away with the parser with the rapid version because as expressions. Have you had feedback from students regarding that? Because I tend to think, and I think most people think that parsing is can be very boring, and that you don't want students getting all hanged up onto parsing in the compiler's course when you really want to show them what comes beyond that. So
Right.
Is that
Amen.
positive? Like is brackets that have an example for this version or not for students?
Well, in some sense, it doesn't, the way I run the course is we don't do parsing regardless of whether students are using Python or
Okay.
bracket. And that chapter in the book is really for other other universities that want parsing. It's there for them. We don't do it. We just always just all parse from the because we like this emphasis on what comes later.
Yeah.
So I agree with you 100%. Here you can see we've got some facilities for printing the concrete syntax or printing the abstract syntax. And it's sort of important that we have both options. The concrete syntax is readable. The abstract syntax is harder to read. It's usually much more verbose. So if you're just trying to get a quick view of did your compiler make a big mistake and output nonsense, you can look at the concrete syntax and see if it's way off. Okay. But oftentimes, especially because we're dynamically typed here, the students might make some tiny little mistake in how they're representing their AST. And maybe forgetting some square brackets or something. And then they need to see the nitty-gritty abstract syntax to debug problems. Okay, so oftentimes we need to have both. All right. Oh no. Tell that to go away. Come back. All right, so the very first thing we're going to do is remove complex operands. So what I'm doing is I'm moving a chunk of code here from being dead code to being live. And so what does this do? It's going to call my remove complex operands pass to produce a new AST. And then, just for this development purposes, we're going to want to look at the output of it. So we're printing out the output. But then here's the important point is we're going to run the interpreter on it and compare that to the expected output. Okay, so maybe we'll just quickly look at that interpret check function here. So here's where we actually run the interpreter on the output of that pass. We're redirecting standard in and standard out, so that interpreter sends the output, gets input from our predetermined input file and is putting the output in a special output file. And then we put standard IO back to where it was, and then we just sort of diff. And what we're doing is we're diffing the output with our what we call the golden file that has the expected results. So, for example, for this sub input test that we're going to be looking at, there's this golden file which says that the output is supposed to be 2. Okay, and actually here let's look at the input as well. And there's the test. So so we're getting our first input 5, second input 3, do the subtraction, should get 2. Print that out. I chose this example in particular because For example, if you mess up the ordering of the side effects, then you'll get like -2 on your output. Okay, so this is a good test case for getting the ordering correct, which is going to come up in this remove complex operands pass. Okay. All right, let me pause there for a moment. Any questions about what we've got so far? Okay. Back to the compiler then. Okay. Actually, you know what? Let's delete this part. And save that for later. So we're going to be getting ready to implement this. The next step is really this grammar sort of driven approach. Okay, so we're gonna, we've got our grammar has expressions in it and statements, and then the top level module. We're gonna want, of course, this remove complex operands is being called on the top level module thing. Okay, slide this out. Okay, so it works. We'll just do this for a little bit here. Oh yeah, that's nice. And then we're basically going to end up with a function for a non-terminal, what we encourage. And then what I'm about to do is to create a match statement here that's going to handle all of these cases, and then another match statement here that's going to handle those, and then a match case down here that's going to handle the module. Okay, so we'll go ahead and do that. We'll start with the most interesting one first. Do match E.
This sort of get easier and more mechanical if were you do it in OCaml, just because like they'd be forced to do the exhaustivity thing. Like you just give the type definition of each IR.
Yeah, I think that's a nice benefit of doing it in like OCaml. Because you'll see like what I'm like down here, what I'm about to do is I'm gonna put like a default case here. Like unexpected. And you wouldn't need this default case in OCaml because you just know that you're already exhausted.
One of the side effects of like going off and giving them, picking the IRs and giving them interpreters for the IRs is one thing they don't get to do in this course is think about the design of the IRs. Yes, the IRs kind of are given to them.
Yeah, that's true. Right, so I'm basically turning, these grammar patterns into match cases. And there we go. So no thinking involved there. Just did the boilerplate. And then actually we can even go a little bit further. Is that I know I'm going to do RCO X somewhere in here. I'm going to do a recursive call like that. Actually, and this thing, you can tell what I've decided to, this is a hint to students about what the return type of this should be. So you're going to get the sort of the new version of the expression. And so we're going to be basically turning, whatever the input expression is, we should be outputting an expression that gives the same behavior, except that it needs to be atomic, right? It needs to just be a variable or a constant and not some big sub-expression. And then the other thing we're returning is, well, all those temporary variables in their initializing expressions. That's what this is, this list of temporaries. And you can actually see I've got a type definition for that right here, which is basically it's an association list mapping strings to or name nodes, I should say, to expressions. Okay. So in what's going on there is that these are going to be this association list needs to become like a sequence of assignment statements. right? But you can't throw down an assignment statement inside an expression, right? So you have to sort of bubble that back up until you get to sort of statement level. And then you can lay down a bunch of assignment statements. So this is, students have oftentimes seen recursive functions, but maybe they haven't seen recursive functions where we really need to produce two values as a result instead of just one. Okay. And then in a minute here, we're going to add another parameter so that we can also communicate information down as we go along. Okay. All right, so here we've got new X and our temps. So we don't really need to, I tell the students, don't think too much about just do these recursive calls. And everyone, I'm going to make mistakes. So part of your job in the audience there is to help catch my typos. Okay. Oh, so I brought up the grammar to decide what match statements to go to. But then the next important thing is to look at the grammar of where we're headed. Okay, so here's the grammar for the output of this pass. Okay. Actually, this is the time to talk about this. And so actually here, let me just bring that all the way up. So this grammar is capturing a new invariant in the AST. It's an invariant where, like, if you look at one of the binary operators or unary operators, the sub-expressions are these atoms I was talking about. Okay, which is just constant or variable. But notice there are still places where you can still have expressions. Like in an assignment, you can have an expression on the right-hand side still. And also, this expr statement in Python is it's the statement that does the side effects of this expression and then throws away or ignores the percent value. So that's what expr does. Usually, this X is producing only a none value, so it's fine to throw it away. But if it doesn't have. Right, and then, but then, like, for example, on print, that does need to be. Yeah. So the purpose of, one way to think about this remove complex operands task is that it needs to get us into this grammar, right? Whereas the initial programs are not necessary. Right. Questions about that?
Where's this grammar style?
I added it recently. It's in the Python student support code.
Is it top level?
It should be in the top level. Maybe did I?
I see a direction. There's the lark / grammars, which has like common dot.
No, I might have. You know what? I might have forgotten to do an add. This is a new thing that I just. Here, I'll push it now. Just to double check here. Yeah, okay, try now.
Oh, there we go.
Yeah, okay, good. Yeah, I think I forgot to do an add on that one.
Right, and what's the source file we're looking at then?
You mean like the test program?
Yeah.
It's the subdirectory tests and then bar. So this is like the L for the LVAR language, and then sub input is this test that we're kind of going to be focusing on. Gosh. So like if you've got like a bigger screen, here I've got the font size up so it's easy to see, but on your bigger screen, I would encourage you to have like this grammar sort of off to one side so you can have, and and also the source grammar in view. Like have both of those grammars in view. And then have another window with your remove complex code that you're implementing, okay? So at this point, I'm going to go back to the compiler now. And we can talk about maybe how to implement. Okay, what do we do for constant? Got our return type here.
Which is the target language we're in?
The LVAR mon. Mon is for monadic normal form. If you haven't heard of that IR format, it's not so scary. It's if instead you've heard of ANF or a normal form, it's almost the same as a normal form. There's very small little technical difference. A normal form, which of course is a really common style of IR.
So like constant just goes to constant, I guess.
Almost, yeah. So the first, we need to return two things, right?
Oh, right.
And then
an empty list of bindings.
exactly, right. Right, and then for name, right, so this is the use of a variable. Same deal there, right? Those things are already atomic. So actually, I'm going to change the return type here. Let's just put atom there. Okay. So we're going to have this invariant. And the idea there is that like if you were to do all the assignments that are in this list first and then run this atomic expression, you should get the same result as the source expression. And so that's the invariant that we want. And sort of that's trivially true for now for constant and var. Okay, what about call to input int? Now we're going to eventually compile this into a call to a function written in C. Right? No, it's going to be an x86 call to runtime. Does that? No, can I do this? So I need to generate a temporary, right? Because this thing's that's not atomic, is it? Okay, so scratch that. So we're gonna need a temp. So that's a name node with I have a utility. There's this utils file. With this generate name function here. Call that. In the bracket, you do gensim. Okay, so we create our temporary. And then down here, we're going to need we're doing this association list where we map our temporaries to the initializing expression. So that would be like so, I think. If you wanted to, you could actually return these instead of doing an association list. You could literally put an assignment statement here if you wanted to. That would be an alternative way to do it. I turn these things into assignment statements higher up. Any questions or concerns at this point? All right, let's do unary. So here's our first where we have a recursive call.
One to look at is like there's stuff about looking to generate. It's not enough to know from the grammar what you do. Right, like you said like a completely like well-typed, reasonable thing that could be output, and like that wasn't right because we're trying to kind of do this. How do you guide the students to know what are the invariants that they're supposed to be enforcing at each stage?
Right, so the other part of the story is those are the interpreters, right? So they need to be thinking through like what happens when I interpret a unary op? And then versus what happens when I interpret whatever I'm producing.
So like the interpreter is like a executable specification.
Yes,
Is there also like an English language specification that you have for
No.
them, or are they
no,
got it? So and that's I guess in part because they're kind of figuring out what the point of these things are. So they should.
yeah, and I guess this is a little bit my own bias being a PL theoretician that I feel like the interpreter is a more precise way of communicating.
Oh, so you're expected not just to run the interpreter, but to read it.
Yes, absolutely.
Got it.
And that's why the interpreter code is literally in the book. Like, even though it chews up a lot of space in the book, like the interpreters with every line of code is like in the book. So they definitely need to read it. That is actually a challenge of getting them to read it. Oftentimes it's like too long, didn't read kind of. But I try to encourage them to go back and refer to it.
Where is the I see an interpreter for LVAR, but not for LVAR.
That's because I do sometimes, just because there's just so many different IRs, sometimes I just say, oh, it's the same interpreter. So it has the same interpreter, but a more restricted grammar.
But if you're reusing the if you're reusing the language of different, like you need different, like if you need to know what you're supposed to be doing when you go from stage A to stage B, right? You sort of need the specification for the output language at each layer.
Yeah, and you get that, right? Because so that LVAR interpreter also gives us the right executable runtime semantics to LMONVAR. And then the only other thing about LMONVAR is that they need to follow the grammar. I think those two pieces do give you a complete specification. I do agree.
So the getting rid of the complex, like this particular thing of like, you need to in fact introduce a temporary variable that will be enforced by the interpreter, you're saying.
No, it's enforced by the grammar. Right, so if you look at like the grammars here, like when you create a bin op, like the sub-expression better be an atom.
Oh, I see. It's not enforced at this node. It's like later down, you won't be able to write the function here. It's not. I see. Okay, that makes sense.
Right. So in a moment here, we're going to want to write we're going to want to create a unary op, right?
Right, and that's where you would run into the mistake.
Right. And if the thing we put here was just like X, that would be a mistake. Right, because it wouldn't follow. But doing like new atom, that's fine. Or maybe let's call it just atom for now. All right, now unary op, again, looking at the grammar, is not an atom itself, right? So we have to do the temporary generation. Right, we're going to want to do this again. Generating our temporary, and then the temporary is going to get the result of the unary subtraction. And this is okay. So All right. Everyone needs to help me out here. Did I make any typos or mistakes or? One good double check to do is, is there any data that got created that I sort of accidentally dropped on the floor? Is there any data that got created that is like not making it into the output?
Sorry,
Temps. Yeah, okay, so we need to do something with temps, right? So temps was all the temporaries that were generated in that sub-expression. Right, so where do those need to go?
You have like concatenate them.
We need to concatenate them. Now, there's a question of, do we concatenate them in front or on the back?
I think it's depends on the semantics of the ordering of findings.
And sort of what we do at the end with our bindings, right? But maybe if we want to sort of have the bindings in the sequence that they're gonna get laid out, then we want it in the front, right? Yeah, so temps plus. So we're gonna append them at the front. Right. And this is, right, so this will be keeping the right ordering, like temps might have, those initializing expressions in the temps might have side effects. So we need to make sure that they'll know we're keeping the ordering of all those things, in the right order. So that actually comes up in this next one. So let's say we're going to do add. Add's going to look kind of similar. Okay, now we don't just have temps, we have temps 1 and temps 2. And here there's there's a question of like, what ordering do we do those two sequences? And Python semantics is left to right execution. So we really do need to put temps 1 before temps 2.
I apologize for only asking questions about how this would work in Camel, but
That's fine.
like to what degree, like there's a bunch of stuff where people have to think pretty carefully about, like what are the rules and invariants and stuff what's going on. And one game you can play with a Camel version of this is you can decide like how hard you want to push on the types to encode those rules, and you're writing by types and they're not.
Yeah.
And so like,
Yeah.
is that like,
would
that pedagogically good or bad? Like, would you want to give them like a floppier set of types where they have to figure out the invariants?
Right.
Or would you want to really like
Yeah.
tighten it down and then like, oh, they'll get it right?
I
After
think
bashing their head into a bunch.
I think it'd be a fun experiment to try to encode like everything that I'm currently encoding in the grammars. Like this thing about atom versus atomic versus X in the, in this grammar. To put that into the types. I think that would be an interesting experiment. I have a feeling that would be helpful for students.
Because there's like a bunch of there's like a non-local thing like in the code where it's like, oh, this thing I get back. Well, I'm assuming that's an atom.
Right.
And like, why is that an atom? It's because the thing for the actual
Right. And like,
purpose
so
of-
here I just,
just kind of say it.
let's just say it. And that gets you, I think that will get you a part way. There's still things where they're gonna have to think about the interpreter and the runtime. Anyway, even after you do that, they'll still have to think about that as well. But I think it is an interesting trade-off to make. Like this thing about what order do you put these two things in? That's something that's an entirely dynamic semantics kind of thing. Good. Okay, let's do sub is almost exactly like add. sub there. Wow, cool. That's it for the X one. We still have to do these statements and then wrap the whole thing up. Put a bow on it there. We're at coffee break time, I believe. So maybe we'll go ahead and do coffee break and then we'll come back and do the couple more cases we have to do and then hold our, cross our fingers and run it and see what happens. We're going to get all kinds of bugs and I'm going to get stressed out about debugging, but you guys are going to help me. Okay? Cool. All right. For those online, we're doing a half-hour break here.
So I searched around for Andrew's GitHub and did not find it.
Okay.
If you find
Send me email. I can hook you up.
Hi, Jeremy.
Hey, how's it going?
Yeah, I'm doing better now.
Yes. Yes.
Oh, yeah, this is your look. You look.
Oh, really?
Yeah.
Yeah, I probably did. Yeah. Yeah, thanks for it. I got over that distance.
Yeah, you can come here. Yeah, I'm sorry, I have to miss some lectures, but maybe I can, well, in fact, I haven't read chapter 2 and chapter 3, so I shouldn't have missed anything, I guess.
Yeah.
The book has it all. Yeah. Hey, I'm totally new to compilers,
Okay,
but I'm an API programmer and I'm familiar with someone else's work at Indiana State. And you Aaron Shu.
Yes. Yeah. Very good.
Yeah, and while you are explaining, I was trying to play around with the sub input expression APL, and I'm not sure what should be the input and output of your RCO program. It doesn't.
So
So
like, what is it going to look like?
right. So what's the flow? So the program would take in the sub expression, and what's the expected output?
Great question here. So we need it to follow that grammar, right? Which means, for example, this whole thing has to be an atom, right?
Okay.
So maybe we need a temporary for that. Okay. And then also, actually, let's call that T3. And then these sub-expressions of subtraction also need to be atomic. So that needs to be right. And then this one as well. So that's what we're expecting.
Oh.
And then we're getting close to be able to run it and see if that's what we get.
Oh, so you're just assigning, you're reassigning those outputs to variables, and
Yes.
you print out the result.
Yes.
And should the print be T2 or T3?
It should be T3.
Okay, just making sure.
Very good.
Okay, I see. Yeah, because in APL we have a lot less types to think about. So I was looking at the type signatures of the Python compiling program, and I'm not exactly sure what's going on. And are they just those expert types? Are they just strange under the hood?
They are classes, Python classes. So there's a base class called expert, and then all these other things in the grammar. So if you look at there's a class called call. There's a class for every one of these things. And so this is actually this is just what it looks like to call the constructor.
Okay.
And, so there's a name class, there's a constant class.
I see. So the name class is what does the name come in? So I'm assuming that the name class is constructed by passing it a variable,
A string, yeah.
a string.
Yeah.
Oh,
Yeah.
so what does the name with the string? It turns the string into a variable.
No, it just sticks it in the field and pulls onto it.
Oh, okay.
That's all.
Okay, let's see. So you are pass. So your program takes in those input. Let's say input file. Yeah, sub input pi and then you try to reorganize those inputs into classes for constructors, and in the end you do some processing and then you put it back together into those T1, T2, T3s.
Oh, well, so when I wrote the output down here, the expected thing, I mean, I was writing what's called the concrete syntax. I was just writing text. But what I really meant was we don't actually generate the text. It's just going to be an abstract syntax.
Oh, I see.
Okay, we're going to live in abstract syntax until we get to the very end.
I see.
And then you finally spit out text in x86. Your x86 program gets written into a file at the very end. But in between, we're just going to be, it's always abstract syntax. It's just that it would be very verbose for me to write the abstract syntax. So I usually
I see.
write it this way instead.
Yeah. I wonder what Aaron's approach will be to this. I know he's a building a compiler himself.
Yeah, it's Aaron actually attended the PLDI tutorial and had fun. He asked all kinds of great questions. So I think he likes sort of this incremental and nano pass style. But I think he does have a much different way of structuring some of the things to adapt it more to APL. A lot of the details would be, the actual nuts and bolts of how he does ASTs and how he writes these passes, I think is rich. But I don't know much about those details.
I see. Yeah, I'll be seeing Aaron at the APL conference next month. Yeah, in Denmark. So yeah, I'll ask him about how he approached this compiler tutorial.
I'm gonna go get some coffee.
So when you do APL, it's like a compiler or is like an interpreter?
Yeah, at work, I never compile my program. Yeah, what I do is I mostly manage the data at my company. So we get.
So your company is using APL as a working language for your projects?
Yes, yeah.
Oh,
so
that's cool.
yeah,
because yeah, that's very cool.
Yeah, the data APL is very embedded in the data pipeline at my company. So the goal is to publish reports on the global economy.
Okay.
And so we have to buy data from data vendors and store those data, transform those data to do some analysis, visualize the data by generating a plot. And all of that is done in our in-house APL system.
So your APL, so in fact, I've only tried APL. I never use it in real pro, and I know that dissertation written by Sue. Yeah. So, So in real usage, practical use of APL, what's the performance of the number?
Performance. We have performance issues, but the APL was not the bottleneck.
It's not the bottleneck. Okay.
Yeah, it's the issue was our legacy data storage system, which is basically reading files on a remote server.
Okay.
And yeah, that's not.
So it's like the network is a bottleneck, but the computation made by the APL is not. So it's not a baby.
Right. Yeah, I never run into data. I never had to wait more than maybe a couple seconds to wait for.
Yeah. So it's not like in the neural network computing, and no matter it's training or inference anyway. So it's just because in neural networks usually that's the most time consuming part.
Yeah,
to
you
do
have a
those
lot of data.
computations. Yes, but in your usage, you don't need to worry about too much about those part of computations.
Right, yeah, our company has like 32,000 data sets to think about. And yeah, it's AP, I never have to worry about how APL is. I can basically process the entire. So we also have an SQL database, and what I do every week is I grab all the data, I load all of the data from the database into my APL workspace, and I just I do some checks on it, and then yeah, I don't feel I never have to wait for more than a couple seconds to do like a huge mapping over all the data and stuff.
Recently, there is another machine learning book called The Little Learner just published. Yeah, so that book, in fact, that with the method given in the book, in fact, Null Scheme has a package for doing APL style computations.
Oh,
yeah, so it also has now with that package, Null Scheme can do like rank polymorphism.
Oh, I see. Yeah, I think.
But it's the performance is the issue now. Right? If we are going to use that for like a neural network training, it will take too long because of the performance issues. So it's so that's why I'm wondering how the performance of APL.
Oh, yeah. The implementation I'm using, Dialog APL.
Yeah.
The company has put in tremendous amount of work to optimize the.
Also, you have like a customized APL. It's not like the standard version.
Well, it's the industry standard. This a particular implementation. There's like it has the most users. Yeah, what Aaron is building, Aaron is also building his own compiler called Defense, and that also has a lot of performance considerations in mind. Do you see Aaron around in Indiana?
Not really. I don't know if it's still in Indiana because when I arrived last summer, I don't know. I guess he has already graduated.
Oh yeah, he's working with a Dialog now.
Oh yeah. So I didn't have a chance. I know his dissertation. I know his name. It's just I didn't have a chance to meet him.
Yeah, I derive a lot of my APL opinions from watching his talks.
Oh yes, because recently, I think somehow PL world has more focus on APL or APL style of computation. There are some in this week there are some talks about about the type safety or the rank polymorphism or some array operations.
Right.
Yes.
Yeah, actually, I was on day one there was a talk by Nini about typing tabular data, and I was the one that was asking about how do you do rank polymorphism like in APL. That's not. I don't think she's onto that yet.
There was a dissertation, about type APL, but it's fully dependent type language, and I think that student that he just stopped developing working on that language after he finished his dissertation. But but there are. It combined many interesting ideas about dependent type together with the APL style rank polymorphism. But the only problem is with such a system, you have to write very complicated types. Yes, it's not like that's why there is another talk on Tuesday or Wednesday. I don't remember, but it's it has no rank polymorphism, but it put forward a simpler type system that it does not work like a dependent type system. It's just a very syntactic comparison between different terms. Such kind of system to gave some guarantee to the shapes, but of course that's not strong enough. But I know that APL do not. I think APL does not use types.
Yes, APL's approach to types is keep it as simple as possible.
Yeah.
So yeah, in APL we have we only need to worry about three things: numbers,
Yeah.
characters,
Yeah.
and arrays. That's all we deal with in APL. So it's a I don't have, and if you want to represent other data structures like dictionary, hash maps, those things, we can use the array representation as kind of a code basically.
Yeah.
And to achieve those same features.
Yeah. So yeah, that's why APL does not have the recursion. So you don't need to write the recursive function.
You can, but
Okay.
I don't write down in production.
Yeah.
There are small use cases. There are a couple of instances of recursion in APL. But yeah, usually the most what I use most often is maps.
Oh yes, yes,
Yeah.
because APL with, I guess in APL recursion, even if it has recursion, it's not the recommended way of programming.
Yeah,
But matrix operation is a recommended way in
Right.
APL, just like in
Yeah.
MATLAB or any other tensor libraries or language.
the recursion function
Yeah.
in APL is, I think it's a relatively new feature.
Oh yeah, because yes, when I learned about that, I heard that there was no recursion because most of the operations can be performed by just using matrix operations, rank polymorphism, so that people don't need to write explicitly recursive functions.
Yeah, true. Yeah, I think there's it saves some memory.
Yeah.
In when the array we are dealing with is too large, but our modern machines are good enough, and I think APL the old way to deal with those recursion problems was also to use GoTos.
Oh yes,
Yeah.
of course. Goto is just like the assembly language or some.
And
so
it makes the code a lot harder to read.
that of course makes the control flow very confusing for everyone.
Right.
Yeah.
I still see a couple of GoTos.
So your code base, I guess it must have run many years.
2 decades.
2 decades. Wow, that was a long time.
Yeah, and it lasted. Yeah, I think it says a lot about APL when the company survived through COVID.
Wow.
Yeah.
But COVID, since your company have like 20 years, right? 2 decades. So even before COVID, your company can work well. You can make a lot of profits. So COVID shouldn't be a problem.
Yeah.
You have so
It's
many
done well already.
Yeah.
True. And the COVID also brought about working from home. And my senior programmer, he's been an old-time APLer. He's been working from home well before the pandemic. So he was working from home before it was cool.
Oh yeah. So I've never met. So you has Sue graduated, right? Yeah.
I think Aaron graduated.
Aaron graduated, but is he working as some developer or as
He's working at Dialog, doing research. I would assume.
The Dialog is a company.
Yes.
Oh, okay.
APL has a funny licensing scheme where you can download the APL IDE, the interpreter, for free. But if you want to make money with it, you
have to buy some license.
Yeah, it's okay if you use it internally, but if you are shipping a product with APL, you have to buy APL. And I think that license complication was holding APL back in a sense, because
but its ideas has prospered in many different libraries and languages, like in NumPy, MATLAB, Python, TensorFlow, PyTorch, the idea of rank polymorphism is everywhere now. Just the people don't know. I think just people don't know that it came from the APL language.
Yeah, a lot of things that came from APL.
Yeah.
Without people knowing.
Yeah.
Like IOTA, which made it into C++.
Yeah.
Yeah, I can literally type IOTA
Yeah.
APL and it will give me a range of numbers.
Oh, yeah, I know that function. That function is really trouble for this type system. It
Oh.
really makes IOTA. It's really,
Oh.
really, that's one of the troublesome things in APL
Yeah.
that makes it hard to give a good static type system to APL.
Yeah, because you cannot expect the size of your output. It's like you
Yeah,
need to be
it's,
dependently typed.
Yeah, that's why dependent type system is required for such kind of
Oh,
for
yeah.
such kind of language.
I see.
And another is like the filter. It's any function that changes the shape of an input. That's a problem.
Yeah, change the shape. Yeah,
Yeah.
you can. Yeah, what type? I guess a map. I think a map is a pretty well typed.
Map.
Yeah.
That depends on. In fact, the map is not the problem. It depends on what function is being mapped.
Oh,
Yeah, maybe some function will map it to a number. It give you an array of like iota. If you are mapping iota, you get result of unknown shapes.
yeah. One thing I do at work is sometimes I want to compare two equally sized shaped arrays. So what I do is not compare. I want to display that side by side. So I have a function that it takes two arrays and basically turns each cell, combines it, makes a two tuple with each cell. So each cell is a tuple of two. And I think that's an interesting thing to type as well.
Yeah, you can, if you are interested, you can check that dissertation. It was last year or it's just called a typed program language.
Ah, I see. Oh, ATL.
Yeah, ATPL.
Oh, HTTP count. Nice. So how did you get into Indiana State?
Oh,
I mean, Indiana U. I don't know why I add state to every US university.
I don't know either. I just came here. So yes, I'm interested in program languages, and I know Indiana University is famous for. It's like one of the famous school in the field of program language.
Oh,
that's why I want to go to Indiana University.
Oh.
Yes, then I got accepted somehow. So I had the chance to come to Indiana University.
Nice.
Yeah.
Nice. What year are you?
This is my second year.
Second year.
Yeah.
Nice. So do you like what did you do in first year? Is it more courses?
More courses. Most
Oh.
of the part were courses, and so yeah. But starting from this year, I have to so finding my topic and working hard on it. Yeah, that's what I need to do. That's why I come to this conference this year.
Oh, I see.
So so your company. So before you work for your company, are you a PhD or?
No, I was during my bachelor's that I got hired. Yeah, I got hired during my bachelor's.
Okay.
And
also you quit?
No. Well, more or less, yeah, because I already finished my thesis in undergrad.
Okay.
And I took all the senior courses as well, but what I'm missing is two freshman courses.
Wow, that's
Yeah,
that's
so-
nothing. Yeah.
Yeah, so I'm just putting it up right now to make some money and pay back my tuition.
Ah, I see. Yes. So that's you have get everything you need. It's just the certificate is not important to you, I guess.
Yeah, and because I'm having a lot more fun working with APL and then school and my school is a pretty long-range school and the PL resources there is very limited. Most of the FP knowledge is from self-study. I just was looking things up myself, but reading papers and stuff.
Oh yes. But I guess somehow everyone entered the area of PL from some in a very weird way.
Yeah.
In a very yes, in a very private way, I
Yeah.
have to say.
Yeah, and the inventor of APL,
Yeah.
Ken Everson, he also noticed this pattern and
Yeah.
one quote from him was, I'm paraphrasing
Yeah,
here, it's a lot more difficult to teach APL at the school. And the easy way is to let people discover and play with APL by themselves.
yes, yes. So if you are interested, the little learner, in fact, have a very gentle introduction to the rank polymorphism mechanism.
Oh, I
Yeah.
see.
But it was introduced in the recursive way. Of course, in the end, you don't need to write the recursive functions, but the internal mechanism is explained with the recursive functions.
Oh,
But yeah,
the little learner.
the little learner.
I see. There's the little,
Yeah.
little everything now. Schemer,
Yeah, all-
typer, prover.
Yeah, everything written by the same author. Yeah, every
Oh.
book. Yeah.
Is the author from Indiana you as well?
Yes, he is my advisor, in fact.
Oh,
Yeah, that's why I know the book.
I see. Yeah. Wait, is it Guy Steele?
Castillo wrote the forward for the book.
Oh, I see. It's just, oh yeah, I see forward by.
Yeah.
Okay, yeah, that's a nice way to gain first offer.
Yeah.
So Peter's your supervisor.
No. He also wrote the forward for the book.
Oh, I see.
There are
Oh,
two
I see.
forwards.
Okay,
Yeah.
there's so many names.
Yes.
Let me guess. So Daniel.
Yeah.
Okay, got it right. Okay, I'll keep it, I'll save that. And the other thing is ATPL, a type.
Program language. Yeah. See if you can find the dissertation of that type.
Maybe.
Northeastern, not, it's I forgot the name of the author, but I know it's from the Northeastern University.
I see. Don't worry. I'm good at looking stuff up.
Yeah.
Google Scholar. Okay, the book by Ben showed up
It's
first.
not a book. It's
Oh,
just
A type.
a type of.
Maybe I need to add the A.
Or you add a
Okay.
dissertation or something. Then you can find.
Yeah, it's really hard to find the APL related stuff on search engines. I've
yeah.
noticed.
Yeah.
So more Western, right?
Yeah, not either.
Oh, Eastern.
Yeah.
Oh my goodness, this is so hard to find and trying every search engine.
Oh, yes, it took me a while to find this one. Yeah. Or you can search Remora.
Oh,
REM
Remora. Okay, I heard of that one.
Yeah, that's a dissertation. The dissertation, yes, basically introduced everything behind the design.
Oh, I see.
Yeah.
Yeah, someone else, I think it was Jeremy Gibbons. He was telling me about this Remora language.
Oh. Oh, yes. If you search that, you can find that Remora typed program language. Then you can find Justin LC tag a typed program language, the semantics, everything. Yes,
Let's see. Justin, by Justin.
yes, Justin, yes.
All right, shall we get started again?
Yes. Is it okay if I ask a couple, if I ask questions frequently?
Sure.
Yeah.
Go right ahead.
Thanks.
Please do. Definitely, this is why you're here in person. Good. Ask away.
Right.
Cool. So, actually, you were at, I just want to, don't know if everyone saw it, but you were asking a good question about like, what is the output supposed to look like from this pass? Right, and so for this particular little example, which is, if the input is, the subtraction of two inputs and then printing, then the output of our remove complex operand should, introduce these new variables T1, 2, and 3, and then we're printing out T3. So that's kind of where we're headed. Okay, now where did we leave off? We were done with RCO X for expression, but we then still needed to handle statements. Okay, so we've got, so we need to do a match on statements here. Give a default case there. Let's go over to the grammar file again. So here's our grammar for statements. So that's going to tell us, what cases we need.
This is the teaching incrementally,
Yes,
and it's going on right now.
yes, we just restarted. Just back from our coffee break. And we're going to dive into the remove complex operands for statements. Now, just copied and pasted the grammar in as usual to kickstart that. Okay, so let's just go and dive in here. We're dealing with print. We can do, of course, we can do our recursive call. So, right on that sub expression, the thing that we're trying to print. And then here, so let's look at the return type of this thing now. We're going to return a list of statements. Okay, so each statement might turn into just one statement, then it's like in a singleton list, or it could be lots of statements, right? Depending on how many temporaries we had to generate for the sub expression, could have been a lot or not. So we'll have those temps, but then we need to add on the code for this call to print, right? So we're going to want to throw down one of these, but now instead of that expression, just do that one down there. So now we're adhering to the grammar for print in our output language. We've got an atom there now of the sub expression. The RCO expression produces, and then we're gonna all these temporaries being initialized, they're gonna go there. Okay, actually I've got a little mistake here, which is that this needs to be a list of statements. These temps are not a list of statements right now, are they?
No, right, because those are environment.
Yeah, it's a association, environment. So we need to iterate over those. So we can do a little list comprehension here. And we need to do an assignment statement. Say it's going to look like that. The AST for assignment statements is a little bit strange in Python. You can actually have multiple left-hand sides. So that's why I've added the angle brackets here, is that this is a single list. We don't, for our little language, we don't have.
You have a little left inside because you're finding a couple on the left.
Yeah. Right. So I think that should work. Okay, now this one's kind of interesting. So of course we need our temps there. We need to do the same deal with our temps. And we might think about taking this and turning it into like a helper function, maybe. Like that for now. I guess now, do we need to do anything with this atom? Atoms are, is a constant or a variable? Look at the, well, thinking back about the grammar. And this, we need to think about the semantics, the Python semantics for this expression statement, right? Which is to ignore the result. But you need to perform all the side effects.
So really the evaluation of the expression gets into.
I'm debating about whether, like, is there, do we need to put anything out here or not? Like we did with the print.
It seems like you should be able to ignore the atom.
That's right.
Just the pointer to the value, and the temps will have the actual thing that forces you to evaluate the side effects.
Yep. Yeah, all the side effects, I mean, because if you think about const and var, neither of those language forms can do side effects. Okay, this is a call by value. And so there's no side effects in atom. They're all in these init expressions. So this is, I think this is good enough. We don't need any extra things. Okay, so that's that. Now let's do the assignment statement.
Does Python have the ability to flag unused variable values? Not like from them?
I don't know off the top of my head. Right, like you might want to do something like, you know, underscore there.
Yeah, I sort of wondering to what degree you want to help the students by capturing more of these things down.
Yeah. Right, and then of course we'll need all those again. This time we are going to need, we need the assignment, right? So we need to do the actual assignment, which is going to use that data that we generated. A little bit worried about using the same name there. Proactively change that. Yes.
What makes assignment different from the expert case?
Well, in the expert case, the result of this expression, you know, if we look at the Python semantics for expert, we're supposed to throw it away. Whereas for assignment, we're supposed to put the result of expert into this variable. So that's what that does.
Wait, is the grammar right? The grammar says a sign can take an X on the right hand side. Shouldn't that be in the atom for alpha?
So great spotting that. That's going to foreshadowing. Okay, keep that question in your head, and we're getting close to being able to run this. And some funny things are going to happen, okay? And we're going to need to iterate a little bit. And it has to do with this distinction, where in some sense we've done a little bit of overkill here. Right? Like this could have been we could have left it as an X, but we sort of turned it into it. I mean, atoms are X's, so this is okay. But it's like we might have turned too many things into atoms. We might have generated too many temporary variables. Okay, and so we'll see that in a second. All right, so let's put the final touches on this. We just have to do a case for the module. That's a list of statements inside of it. I'm going to iterate over all the statements and call RCO statement on each one. That's going to give us a nested list. All right, so the first S is for statement. The second one is for plural statements. And the third one is that it's lists of statements. So that's how I've got this variable name here. And then we need to flatten that, which we can do conveniently in Python with this sum function. Because plus is the pen. Rolling my eyes. Okay. So that might just work. Shall we try to run this? Now the scary part. And let's remind ourselves where we stand with our test system. Right, it's going to call down here. We're going to run. Right, we're going to do the sub input test, and then we're going to go ahead and run remove complex operands. We're going to print out the result. We're going to interpret it and check against the golden result. I don't have an atom type definition, so I better all of that as expert for now. I would need to go define another base class. All right, so here we died somewhere else. M, that should be using X. Should have been P. Program. I put M because I was thinking module. This is where like a type checker would have been helpful. I'm now like type, and we're basically type checking by a runtime. Okay. I want to change these to Adam. I changed the name of these. Let's double check. I didn't make that mistake elsewhere. There we go. So now I have that variable going to there. That one goes there. Better. Woo! Look at this. All right. Do a little dance. It's always good to celebrate the small victories, you know. Yeah, it worked. So that's that. Remove complex operands passed. That means it did the diff on the outputs, got the same result. And we can sort of eyeball this concrete syntax that we got out and compare it to, you know, what we wrote out as like what we were expecting. And it's the same, except, you know, this is a bit more principled. In computer science, we start counting at 0. So, yeah, we're good.
Wait, didn't we introduce an extra? Oh, I see. We did introduce the temp.2 with that extra app that we illustrated. Wasn't there a spot where we introduced an extra atom and we didn't strictly speaking need?
All right, so here let's do a little experiment. Let's take the output, just for fun, take the output program here, which is a valid Python program, and run that as input, okay? And because the situation that you want to see, that you're wondering about, isn't exercised in our first example, but our second example. So I'm going to change our input program. Instead of sub input, I'm going to do sub input. I think it's called flat. We go look at it, test bar sub. Now I just created this file like during the break. Okay. I haven't actually taught it like this way exactly before. Kind of fun. But so here's our essentially our output program, but now as a test program. Okay. And this one now has a lot of variables and a lot of assignments already, and it's got a lot of things that are already atoms. And so what's going to happen when we run that through so I've now changed the input file here. Now I'm going to run the compiler on it. Okay, that's the input. Let's look at the output.
Yep.
Not good.
That's the thing you could fix.
What's that?
That's the thing you could fix.
Yeah.
So how do you get the students? Because this is not part of like, it's correct.
Yeah.
It's gross.
Yeah. Yeah. So, you know, it's like, for example, when they submit this to the auto grader, we'll let this fly. But this is something that we talk about in class and be like, yeah, this is gross. And how do we
You can do a thing where you like run it, run it 100 times on the same input and see if it's like that.
Yeah. And I do talk about things like, well, when you get to register allocation, you're going to be n squared with respect to the number of variables. And, you don't want to be blowing up the number of variables because that's going to kill you later in the compiler. And we could do time limits on compile times or something like that if we really wanted to be mean. But yeah, that's kind of a fun discussion. All right, so how do we fix this? Fix our compiler.
Let me just check if the expression is in Adam.
All right, so
Pattern.
the question is sort of where do we do that? Here, let's go in. Let's sort of stare at our compiler here. Right, so maybe one place to look, is we've got an assignment statement here, and we know that this thing could have just been an expression, but we turned it into an atom anyways. So that's one of the points of overkill. And so what would we need to change about the code here? With this call and what we put there to sort of get this fixed.
Go deeper on the pattern match in the X and see if it's a constant or a name.
That I think that is a first sort of inclination to do that. The problem is that sort of that issue is going to happen at every level, right? That you're going to have to
I think you can do another pass to just flatten. Running that. You could run, but
so in some sense, that's what this pass
but
is
can't you
for.
do it recursively? Isn't it just going to fold in and everything will just flatten away? I think if you do it uniformly and pull in, you should be able to fold this into a single pass. Right, as long as you make sure it pulls things up from the bottom all the way through. Yeah.
How about this? What if, part of the problem is that when we do the recursive call, down inside that call, it doesn't know whether it should be producing an atom or any old expression. It doesn't know because it doesn't have the information from the context.
Sorry, yeah, so we should pattern match on the evaluated expression. Is the point?
Well, we sort of, the thing is, I really try to encourage students to when you're writing recursive functions, don't do nested pattern, don't ever, just do the recursive call and sub expressions, right? And so just kind of stick with that pattern. What I recommend is that we just need to send information down to help the recursive call decide what to do, right? So for example, if we add another parameter, so this is one way to do it. There's multiple ways to do this, but you could add a atomic. Right, to say, does the output need to be an atomic thing? And if not, it can be an expression. Okay. And so then we can sort of change up how we do things. So for example, here, we could say if need atomic, then this is the right thing to do, right? But if not, we don't need it to be atomic. And we don't need to generate the temporary. And we can just do the call. About 10 words there. You have the ideas that we're, sort of communicating down, down the recursive calls, so they know a little bit about the context of where they're being called from, and can then sort of dispatch and do, do the right thing. So we could basically do the same. Same deal for all of these. Actually, some of this code we use. This is where you wish you had just the one primitive op node instead of here. Okay. All right, now we need to look at all of our calls. Actually, we need to look at all of our calls to RCOX and talk about, like, should we be passing in true or false as this extra parameter, right? And we basically need to be thinking about, like, the okay, so here's a call to RCOX inside of the unary sub unary subtraction. So should that be true that we need atomic, or false? Here's the grammar.
Oh, true.
True, yes. Right, so whenever we see like atom in the sub-expression in grammar, then that means we need to do a true in our recursive call, right? Which means we also need true here, here, there, all those. And then what about here? Get into grammar. If we look at print, yep, okay, that one needed to be atomic. For expr though, this one does not need to be atomic. So we'll do a false there. And then for assignment, that's also going to be a false. I think that's it. Did I go too fast, or is that makes sense? There may be other ways to sort of get this job done. One other way is, instead of, it's sort of isomorphic, but instead of a Boolean value here, so let's say you were doing this in a statically typed, like an OCaml. You noticed I changed this to expert, and so now I'm being sort of looser about what's going on here. What you could do is split this into, instead of having the Boolean, you could split this into two recursive functions. One that you call when you want it to be an atom, and the other when you want it to be an expression, any other expression. Okay, and then you could even change the return type. So like, and this is actually how I do it in Racket. So here, let's go look at the Racket code. So in Racket, I have one function that's RCO atom that returns a, so it's, it looks like the one we just created. But then there's also this RCO expression, and that one actually just returns an expression. And it uses let expressions to sort of, instead of assignment statements, it's just wrapping it, the expression in lets. Okay. Good. So yeah, so you can kind of play around with that if you're doing it, if you're in a statically typed room. Okay, shall we run this and see what happens? I know it's gonna break. Ooh. It works. And check out that output now. So good. This one was just sort of identity function on this program. So that worked great. So that's it for remove complex. Any final thoughts, questions, concerns? From a teaching perspective, this, adding this parameter is definitely a sort of a complication. A lot of students aren't familiar with doing that kind of thing with the past contextual information. And also, a lot of times they're not as familiar with returning two different things back up. So that's where this sort of stretches students a little bit.
Do you typically cause them to get this part right, or do you sort of let them not worry about it too much?
I do kind of push on them to get it right. And it's actually like one thing I like to do with the students is we do code reviews in class after an assignment's been done, and I anonymize their code. I'll go grab their code from the auto grader that's been submitted, anonymize it, and then we'll put it up in front of everybody and talk about it. And oh, here's an interesting way to organize it, or oh, here's maybe this was overly complex, this solution, or didn't quite get the job done. So we'll talk through those issues. Oftentimes they'll make mistakes that I would never dream of them making. And the code review is the only way for me to become cognizant of what can happen and what they're doing wrong. And so I find that pretty valuable. Otherwise, I just wouldn't talk about it. And then they might keep doing things a certain way that's like way less efficient or nice. Right. Do we want to, let's see, we've got about an hour still? Yeah, we've got an hour left. We could dive into selecting instructions. That's one thing we could do. We could sort of then switch back into sort of a more overview mode for the rest of the passage.
I'm very curious to understand how the incrementality works now, right? Like here we are talking about this is all about the first 2 weeks, right?
Right.
What we're talking about. These are like the first set of passages. Then what does the process look like when you're like, and now the language grows?
Yeah.
Like, I'm very curious to understand how that, because that's like much of the course is that, right? Like
Yeah.
at the beginning.
Right, that's a really good point. Yeah, so maybe I can just talk to that by like opening up the book and sort of and talking about like maybe what happens in some of the later chapters. Okay. So maybe yeah, let's go ahead and do that. And maybe one thing I'll say is that it took a lot of work on my part to get the chapter ordering right. Okay, because the language features are built up in a very specific order to make it possible to do like later language features, for example. So
I'm also just curious about how the mechanics, like you're extending the grammars, I assume,
Yes.
as you extend the language.
Yeah, so let's.
Does that mean that
let's-
you're extending, like, do you have, like, is part of the checking that people are within the grammar? Or does that mean you like, you move that, you're changing those verifiers over time?
Yes, so we're changing the interpreters and the type checkers. So actually, maybe here's first, let's just look at the grammar. So here's, the next language after LVAR is this LF language. And so what I do with the grammars is you always see all the previous languages in gray, right? That's the stuff that stays the same. And then the things in black are the new syntactic forms that are coming into your language. Okay, so here we now have the true and false literals. We have a bunch of logic operations, ands and ors and nots. We have lots of integer comparison. Integer and boolean. No, I think I keep it to just integer comparison. And then this is Python's, conditional expression. Okay. And then we also do conditional statements. And I mean, all of our same infrastructure is going to make it sort of having both of these is no big deal because it's sort of compile them both the same way. So from a grammar standpoint, it's like, okay, here's the new language forms. Oftentimes what this means is that in the existing passes, you're going to add cases for all the new forms. And you need to think through like how do you deal with those cases. And sometimes you also need new passes as well. Okay, so in terms of checking, let me show you the interpreters a little bit here. So like here's the interpreter for LVAR. And actually you can see that it inherits from LInt. So the chapter 1 has this chapter 1 talks about this even tinier language without variables. That just has integer arithmetic. So this is where we have the interpreter for all the integer stuff. And then this interpreter inherits from LInt. And this is basically a way for me to, I need to maintain, lots of instructor solutions for slightly different languages and lots of interpreters for slightly different languages. So I'm using this inheritance approach to give myself open recursion and sort of extensibility, because it's it's like the expression problem here, right? So this is one way to do it. So by making these things methods, I'm sort of leveraging. So like, for example, when I call interp expression here over here, that's really, since this is OO, object-oriented language, that's open recursion. So that'll pick up like this new name case, come back and hit the derived class and then give you that. Okay. So for the most part, my interpreters can just add new cases and leverage the old ones. And that's good because let's say you try to, each interpreter really only interprets the current language, not anything extra. So you'd get errors if you try to give it some language that's outside the going part. Then there's also type checkers.
And the student solutions are structured the same way. They're also using inheritance for.
They don't have to.
So they can just go off, just edit and extend.
Yeah, they could just edit in place. And there's not really a strong reason for them to do it this way, because they don't need to maintain n different versions, right? They just need to maintain one version that evolves. But if they want to do it this way, it's fine. There's a little bit of overhead to thinking about it in this moment. Okay, so there's the interpreters, there's also the type checkers. I guess it starts with LVAR. So this is just sort of a bog simple type checker that I've written for the LVAR language. And technically speaking, L-var by itself can't have type errors because the only type is int. Okay, so you literally can't. So this is maybe a glorified grammar checker. Okay, but when you get to elif, that's when you've got Booleans and a Boolean type. So you've got two different types of things. And so you can have actual type errors. Okay. But I need to inherit this stuff. So I've got to separate it out. And so when we learn about, so the chapter on conditionals is where we learn about type checking. So that's where like, oh, what is a type checker? And then the notion of your type checker as a precondition to your compiler. Okay, so if you want to think of it that way, that okay, these type incorrect programs get rejected, they never even get fed into the rest of the compiler. And sometimes students have like an urge to maybe like put various guards or checks or defensive programming in their compilers, but reduplicating some of the checking the type checker would have already done. And so I kind of have to, that's a good point to talk to them about. No, you don't need to do that. You got the type checker there and let it do its thing. And then it's establishing lots of invariants that you could then assume are true. Okay. So there's the type checkers. And then so let's talk a little bit about the intermediate languages also have to be extended. Okay. So the rack. Bracket. Let's look at the red one. That's the Python conditionals, interpreter. Type checker. They need to know the type, they need to understand the type checker too. That's why that's there. Okay, so then this is the intermediate language that comes out of essentially it comes out of remove complex, and then there's another pass that we kind of skipped over called this explicate control pass. And then here's sort of the C-level language that now has like, well, it's maybe it's fairly low level C because you've got like go to. And this at this point you learn that so we do this optimization actually on the condition here, where we're looking at like, oh, are you just a true or false? And then we can just get rid of the if altogether. Or are you a negated expression? And then you can get rid of the negation and like flip the else in the then. So you can sort of almost like partially evaluate the condition. But you get to a point, especially if you have like nested conditionals, where you end up feeling like you need to duplicate code, which you just can't do in a compiler. But instead, what you need to do is share code. So that's why the go-to becomes an important thing, and you don't label blocks of code so that you can have code share. Yeah.
Can you maybe give an example of what you mean with that?
Sure. Here's an example. So like here's one of these nasty nested conditionals, okay? And I mean, actually, and you might wonder like, who's going to write code like this? But so it's like, for example, it's a fairly normal thing to take things like ands and ors and sort of expand those out into conditional expressions. And so you can very easily end up with lots of these things, arising in your intermediate languages. Okay, and needing to deal with it. Right. So here, to help you read it, so here we have a conditional saying if x is less than one, then return that, otherwise that. And so those are booleans. That boolean will decide which way to go on this if, whether it be y plus 2 or y plus 10. Right, so you've got one condition depending on another conditional. And so, oh, and then I should also mention that part of the motivation for why we want to get down to a place where the conditions are really just these sort of atomic things, because at the x86 level, we don't want to be dealing with arbitrary booleans. Like, let's say x is sort of an arbitrary boolean, then we're gonna have to compare, like, oh, is it a 0 or 1? And then there's a silly dance you have to do to set the condition code, and then you get to finally do this jump JE or jump if equal, right? And all of this stuff here, like, let's say you already just did a compare to get to the x. That compare would have set the condition code, and then you could have deleted all these instructions. So you really want sort of if, like, to have a comparison right there in your intermediate language so that it maps easily to the x86. Okay, so one way we could restructure this code is to sort of push one of the ifs into the other one. Okay, so this is our same program, but I've pushed the outer sort of into the inner one. Okay, so now we first do this x less than 1, right now on the outer thing, and this is just this nice conditional. This is going to be a CMP compare Q, and then a jump equal, right? And then it can jump to one of these two branches. And then now here we have what used to be the outer if, and then the bodies of, what was the range there, okay? But look what happened. These two branches now, we've duplicated these two parts of the code, right? And that's a big no-no. We can't duplicate code, right? So what you really want to do is you want to be able to share. You want to, in here, instead of having y plus 2, you want to have a go-to, and a go-to here to the same place. So this is y plus 2. So that's the right. So this is what we end up with, doing it sort of the right way. And we have, so now it's like, okay, x, this x less than 1, that's, if you think from a control flow point of view, that's the first thing that happens. That's boom right up there. And then go to block 6 or block 7, right? Block 6 is going to do the x equals 0. Block 7 is going to do the x equals 2. Right? And then those now, either way, you're going to go to block 4, block 5. So those are shared, and that's where you've got your y plus 2 and y plus 3. Yeah. So it actually took me several years to get this part sort of into the compiler course. Because at first I wasn't doing this optimization, I was just generating the bad code sequence for these. Oh, and maybe just kind of show you what the x, do I have the x86 for this? Show you how nice it comes out at the end of the day. Yeah. Like you can see here, like you just had this CMPQ, like this is the is x equals 1, and then jump right after that. That's really nice. But yeah, for a long time I was generating just the naive sort of sequence of instructions, and not needing the go-tos and stuff like that. But then a few years later, I was like, okay, let's try to do that optimization. And then I was like, oh, and that's where we need to shift. And then there's this code duplication issue, and that's like, oh, that's where we need to shift from having an AST, like with emphasis on tree, to a DAG, where we have sharing and we have labels that go to. And so that was kind of an interesting, like, oh, that's why, why do compilers use control flow graphs? Okay, with emphasis on graph as in DAG. And it's really, this is one of the real reasons why you need to do that. I mean, compiler textbooks will often hand wave about like, oh, this is just how we do it. But like, this is a really strong.
So it's a DAG like a tree with pointers to other nodes?
That's right. Yeah, and that's what these labels and the jumps are. The jumps are the pointers to these labels. I mean, in some sense, I mean, you're going to end up with jumps and labels no matter what, because that's x86. But there's sort of also the strong reason from an optimization standpoint why you want to land there. And by the way, this sort of optimization on conditionals, I was talking about Simon Peyton Jones earlier. You know how there's some old papers of his. It's actually this same optimization that they do. They also do in Haskell of optimizing nested conditionals. It's the same stuff arises there. So you have some early papers on that. So yeah, so with each sort of iteration, each additional language features, then you keep getting these extra complications. That's conditional. Let's maybe talk about, okay, then there's loops. I mean, this one's sort of fairly obvious that, we really just add, while loops to the grammar. But then nice picture. I don't have a nice picture. But I really should have a picture of a control flow graph with cycles in it. Well, maybe this one is a good one. Okay, good. Yes, this one has a cycle on it. Okay, so this is like after you've already lowered down a while loop to the sort of this low level sequential layer. So you start out hit block 5. This is like the header of the loop when you're deciding which way to go. Block 7 is the body of the loop. And then at the bottom of the body, you jump back to the loop header. So there's your loop or your cycle in the control flow graph. Okay. And so this is where things get more interesting for the register allocator. Okay, so the register allocator, it needs to figure out, there's a classical thing called liveness analysis. It needs to figure out which range of code is a certain variable being used in. Because if two variables are being used at different ranges, you can put them in the same register, right? So it's like time sharing or something. Your ski condo. So liveness analysis needs to figure that out when what their live ranges are. And you typically do this from the bottom up because you're looking at which variables are read from. And those, if it's going to be read from further down in the program, it's live, and then you match it up with an assignment state, an assignment to that variable, and then it's no longer live after that, above it, unless it gets read. Okay. Then it might be alive in another region. So you go, oftentimes you go back, from bottom to top. And at the bottom, nothing's read, so it's like empty set. And so like down here, when you're done with the program, nothing is live. So you can work your way up, and each one depends on the one prior to that. But then it's like, okay, now you have cycles. So how on earth are you gonna, do the liveness analysis? You've got a circular dependency in your liveness. So this is where you need data flow analysis. You need what you do, you need to sort of go to a fixed point, right? So what do you do? You can take each of these blocks by itself. And you can kick off liveness analysis from the bottom up starting with an empty set. Okay, when you do that, you're not gonna figure out all of the things that are live, but you'll figure out some of them. Right? And you can propagate that to the top of this block. You can do the same thing for this block. Propagate it out, propagate it out, propagate it out. You do one round, and now you know a little bit more information than when you started. Okay. Then what you do is everyone has to talk to each other. And so, like, let's say here you're going to be block 8. So if you're moving backwards, whatever's live at the top of block 8 should be live down here. Okay, so that means you take your current result there, pull it over here, and in the next round, you use that to go on. Okay. And then you get a little more information. You just keep doing round after round of that, of local propagation, global communication, and then you'll hit a fixed point. You'll reach a place where they no longer change, that all those liveness sets at the top stay the same, and at that point, you've got a correct analysis. That's where that sort of classic compiler result comes in. It's kind of fun that we're talking about this in Seattle, because data flow analysis was invented here in Seattle, Washington.
How do you know when you reach the fixed point?
Because what you do is you record what the set of live variables is at the top of each block, and then when you go to do the next round, you remember the previous round, and you just literally just check if those two sets are the same. So it was Kildall, who was the man who he was a grad student at UW when he invented data flow analysis. He also invented an early operating system that was a competitor to Windows, and he sort of famously lost the battle, the operating system battle, and became sort of a bitter man who ended up dying early. It was like the most interesting.
But what's the operating system called?
I don't remember. It's on Wikipedia. That's while loops.
What about lambdas?
Lambdas, yes, lambdas are so much fun. Okay, the story for lambdas is somewhat involved because so we do what's called flat closures, which is like the way Shakespeare and a lot of good compilers do it, where you represent a lambda turns into a tuple with in the beginning of the tuple is a pointer to a function, to the code. So it's a code pointer. And then the rest of the tuple has the values of the free variables. Okay. Now, obviously, I just said you need to use a tuple, right? So that's why this chapter has to be here before we get to lambdas. We have to introduce tuples, and we need to introduce garbage collection, because those closures actually have to get garbage collected. So that's why tuples is here. But let's just for fun kind of skip over tuples. And by the way, I go over what kind of a copying collector. So it's perhaps one of the simplest collectors. We give them the code for the copying collector that's been written in C, but they have to interface to it. And there's a bunch of interesting things you have to do from a code generation standpoint in terms of calling conventions and making sure certain things like your live roots are visible to the garbage collector and the server. So there's a bunch of things the compiler has to do, right, to communicate to the collector. So that's what they have to deal with on the compiler side. So after tuples, we do functions. And by functions, I mean C-style functions. So if you look at the grammar here, functions are top-level definitions. Okay, But you can, but we also, you'll see that there's a callable type here, so that's Python's way of saying function type. And so because there's a function type, that means they're sort of first class in the sense of you can pass functions around. Okay. And it's a function pointer in C terminology, right? And you need that for closures because, I talked about putting that the first thing in the tuple is going to be a function pointer, right? So this is laying the groundwork for exactly what we need to do closure conversion. And this is where, so we introduce these kind of functions. This is where we talk about a lot more about calling conventions and how you pass parameters. We even do efficient tail calls in this chapter, which is kind of neat. We added that just a couple of years ago. Grad student Michael did that, which is great. And then we get Lambdas. Let's jump into Lambdas here. So here's a good picture of what a Lambda looks like, and here's the code. Can you read that, or is that, or should I?
It's a bigger.
Okay, I can split the screen here. There we go. Okay. This is a great little example for teaching closure conversion. Okay, so here we have a function f that's going to return a lambda. Okay, so it's returning function from integers to integers. Okay, then down here you have two calls to f. Okay, so we're going to create two lambdas. Right, so the first lambda we're going to put into this g variable, and the second lambda we're going to put into h, and then we're going to call. Oh, and notice that we called f with different parameters, different arguments here. That's key to this example. And then we're calling g and h with different values as well. Right. And so now let's look at down below here. We have the memory representation that, once their compilers do everything that it's supposed to do with the closure conversion, this is what the memory will look like as it's done. Okay, so the code over here, the squiggly stuff, imagine that's the body of this lambda. It does the x plus y plus z essentially. Okay. We can get into more of what that looks like, but this tuple here with the function pointer and the two values, this is what we refer to as this flat closure representation. And notice that we only have the variables that actually get used in that, and not variables that are up. There could have been lots of other variables in scope, but we don't need them, so we don't put them in the tuple. Right? So this is actually a great example of why you need to understand how to compute what's called the free variables of an expression. This is why you have to compute the free variables of this lambda, right? It's all the variables that appear in this sub-expression, but aren't defined, right? So it's x and y appear, but there's no definition for them, so they're free. Z appears, but it also has a definition, so it's not free. Okay? So the free variables are x and y. So that's why we need two slots for x and y in our flat closure. And then you can imagine, okay, now let's step through this. So we call f with 5. So x is 5, y is 4. So when we execute this lambda here, what's happening at runtime is that lambda is allocating this tuple, filling in 5 and 4 there. Okay. And setting up this function pointer to what is then going to be a globally defined function to do that code sequence. So that creates this thing in memory. And then we call f again. And this time, x is 3. So we get a 3 there in our closure, black closure. Right, and then let's think about what happens when we call G11. Okay, so that's the 11 is going to go into Z here. But then, so when we evaluate Z, okay, that's easy to understand what's going to happen there. That's usual calling convention kind of stuff. But what about X and Y? How do we arrange to communicate the 5 and 4 here from the tuple into this code? And this is one of the special things about closure conversion dance. Let me see if I think I have the code for this. What happens exactly? I get to the closure conversion paths. Here we go. Here's the closure conversion. Okay, good. So yes. Good. Okay, so here's the whole, this sort of tells the whole story here. This is figure 9.8 with the Python side. So part of the story with the closure conversion is, well, how do you turn this lambda into a globally defined function? Okay, and so here this lambda 0 is that globally defined function. And notice that now we've added an extra parameter. Okay, it still has its z parameter, but now it has this extra parameter that's going to receive the closure itself. Okay. So it's going to be this tuple. I'm punting on giving it the function pointer type. But then the in this example, it takes an integer. And then you might think, well, why is this? It has to do with the assign. Oh, this is an assigned variable. So since this variable is being assigned to like a mutable variable, it gets boxed. Okay. So that's how we box them with the tuples. But the main point here is that we've added these, instead of just x plus y plus z, we've added these two lines here now that say, oh, we can get the values for those free variables out of that tuple, out of the closure. Okay. So we read our x and y, our free variables out of the closure, and then the rest of the code can run as it normally would. So that's how we transform body of one of these lambdas. And then the other half of this is, well, what happens when you call a lambda? I mean, yeah, a lambda. Like, let's look at this G11. What happens when we call G11? So that's down here. Okay. And so what we're doing here is that G now, right, when we evaluate this G up here, G is going to produce a closure, right? Which means it's a tuple. Okay. So we get the 0th thing out of the tuple. That's our function pointer. And we can call that, right? So this is now a function call. And we've got the argument 11, that's going to go over here. But then for that first parameter, which is going to go into this FVS, this is free variables parameter, that's the, right, this is where we're going to put the closure itself as its first parameter. This feels sort of circular, and it is. I'll pause there for a moment. So this is a pretty interesting pass and that there's a bunch of moving parts. And it's all this sort of symphony or choreography that all have to work together to make the whole thing work. There's lots of transformations happening at different points in the AST. And I feel like this is almost like the climax of the course right here, because so many different pieces built up to making this be possible.
How does this actually like, how well do the students do at this part of the, that's like, what are the problems that you run into with teaching people this stuff? How do they get, how do they deal with, you know, adding some like such a big complicated chunk to this thing?
Yeah, this is a hard assignment. I mean, it turns out that the actual amount of code that you have to write for this assignment is relatively low, but it's sort of conceptually. And so these like little examples like this that I've got, I think are crucial, where they can sort of iterate on that, and they can see that they've got it wrong, and sort of stare at you know what the output's supposed to look like, and they can iterate on that. Finally get it right. One other challenge though is that sometimes they still have undiscovered bugs from earlier in the compiler, and then find out like if they screwed up something with tuples or functions, then they might end up exposing that when they're working on Lambdas, and those are extra painful to debug. This is a hard course. and you can see how like by the organization, I'm trying to make it easier, but even so, it's hard.
When you add these new incremental slices, do they tend to be like focused on some, like there's like two dimensions of growth, right? There's like the set of micro passes, and then there's like the functionality that you're adding.
Right.
Like is it structured that when you add a bit of functionality, it tends to be focused on like a smaller subset of the transformation stack, or like, you know, when you add something like Lambdas, are you like doing like a lot of hard work the whole way down?
Yeah, so it totally varies by feature. And one way you can kind of evaluate that question is that for every chapter I have sort of this diagram that shows you all the passes, right? And you can see whether there were any new ones, okay? And so like for this one here, this convert to closure, well, there's convert assignments and convert to closures. Those are the only two new passes. So all the action for closure conversion happens here, right? It used to just go reveal functions and then limit the function. So it was like, so you're just inserting these two passes here, and everything up here has to now have a new case for Lambda, but those cases are pretty easy to deal with. You just sort of do the recursion kind of thing. So this one is sort of an example where there's sort of a localized change that has to happen. You know, in terms of like just those two, because right, once you hit funref here, this language, this is the, you know, the C level language of functions, function pointers, you know, that's just, you know, the work you did in the previous chapter, which you will put down. I think I'm trying to think of a chapter where there's more changes like throughout. I think that the functions chapter is probably, chapter 8 is probably a good example of that, where, okay, there are some new passes, you can real functions and limit functions, but these passes are not all that interesting. And really, the interesting changes are having to do with like calling convention kind of stuff. And so that's going to happen. I want to say that happens in preluding conclusion. And then also there's a lot of new instructions. So you're doing new things in select instructions. The register allocation is now happening, not just once for the whole program, but now you're doing register allocation on a per function basis. So you can't, I mean, this diagram doesn't, talk to that stuff, but if you, so each chapter will have like a description of what needs to happen. So for every pass that has like non-trivial changes to that pass, then I'll have a description of what needs to happen and these examples. So you see, you see that, for that particular chapter. Yes.
I see at some point in your classes you are changing the large lambda to C then to x86. And you are and those I guess transitions have what aspect is controlling the select instruction. So is there anything fundamentally is there any fundamental transitions going out such that you have to change the letter from L to C?
Yeah, so that's a great question. And that so the transition from I've got abstract syntax trees with no sharing to control flow graphs with or graphs, or especially in while loops, you have graphs and potential sharing. That's at this level. So this transition here that happens in explicit control is what in the optimizations on control flow that we talked about. That's what necessitates this going to this graph format. And that's really the big difference here is that you've got more of a graph format here. You've got labels and jumps.
So
in
tree to graph.
Yeah, data structure changed there.
Oh. What about from C to x86?
So so select instructions, that's that where you're really bridging from having programs like x equals y plus 3 into like, oh, I need to do an add queue instruction. Right. So that's that distinction there. So here you've got an IR that's kind of fairly regular and easy to read. And then down here, you're like, oh, now I'm dealing with the peculiarities of x86.
Oh, okay. So that's why you switch to following the x86 standard.
Yes. And I should also mention, this is reminding me that this is also where the select instructions is where we start to deal with some of the calling convention kind of things. Like, okay, your parameters, some of your parameters are coming in as registers. Right, so like in explicate control, well, not in CFUN, functions have parameters. Like, and that's something that the language takes care of, it's parameter passing. But at the x86 level, x86 doesn't have a built-in notion of parameter passing, right? That's what the calling conventions are for. So we end up having to generate a bunch of like leading up to a call queue instruction, there'll be a bunch of instructions that move things into the particular registers that are used for parameter passing. And then like at the top of each function body, you'll see like a bunch of instructions that are moving from your parameter passing registers into whatever local variable or for them. Right.
Isn't that sounds pretty? Yeah. So that's when the program reveals this true form.
Yes. A little bit tempted to spend a little bit of time talking about register allocation. We haven't kind of skipped over that. And it's one of the more fun aspects of I think of the book. Part of it's just like this classic graph algorithm. And then also the way it ties in with Sudoku is really fun. Back to register allocation here. So maybe this is a place to start the idea. So here's one of these x86 programs, but it still has lots of variables in it, E, W, X, Y, and Z. And then, and we figured out like which things have to be alive at the same time. And that's what it means to interfere. So like, we figured out that X and W, like W was just written to, and this can be read down here, and now we're writing to X. So there's no way these two things can go in the same register. So we say they interfere with each other. And so that's why this graph captures interference by there's an edge whenever two variables interfere with each other, right? And very quickly and easily look up, when there's interference. Right. And so now this notion of register allocation becomes graph color, where we're trying to assign a color to every node. And if you're adjacent, then you can't get the same color. Right? So that's sort of this classic thing. Now, of course, it turns out Sudoku is also graph coloring. Okay, so the correspondence is that each tile is a node. The numbers are colors. And then if you're in the same row, that corresponds to having an edge between, it's like you have an edge between all of those. So there's a lot of edges. And I haven't shown all the edges over here. You wouldn't be able to read the graph if I had all the edges there. So, and if you're in the same 3 by 3, you all get edges between you. And if you're in the same column, you're fully connected with everyone in the column. Okay. So that's how you turn Sudoku into graph coloring. But the fun thing is actually to then say, well, can we use Sudoku techniques to do graph coloring? Okay, so I don't know about you all, but like when I'm glad that my phone app for doing Sudoku lets me sort of do note taking where I can fill in like which things are still possible, which numbers are still viable, which ones aren't. Right? You could fill that in for all the tiles, and then you can look for like, oh, is there a tile where there's like only one option left? And it's like for that one, it's like great, pick that, right? And that's like in like the AI literature, that's like a most constrained first heuristic. Okay. So that's a great way to go. And that also corresponds to, in the graph coloring world, that corresponds to an algorithm called saturation-based coloring, where like if you think about color saturation, the more adjacent colors there are, the more saturated you are, and you're more constrained. Okay? So that's what you do there. In some ways, though, playing Sudoku is harder than graph coloring, because in Sudoku, you like let's say you sort of end up reaching a dead end because you didn't think hard enough about your Sudoku board, and you have to backtrack, maybe, God forbid, right, to try to get it right. I mean, I know that like you're supposed to always be able to, if you reason about it hard enough, you should never actually backtrack on a Sudoku board. But let's say the algorithm that we're going to use to implement this is like simple, right? It's like just the pencil marks, just the saturation-based coloring, most constrained first. But it's like, do we want to backtrack in a register allocator? No, we don't, because backtracking like that can go exponential. Right? You do not want to go exponential time in your compiler. So what can you do instead? Well, here, for Sudoku, you only have 9 colors, right? But in the register allocator, yeah, you only have like 15 registers or something, 16, I forget. But you have stack locations too, and you have any number of stack locations. So what we do is we use numbers for locations, and the first 16 numbers are like correspond to registers, and then the rest of the numbers correspond to stack locations. Okay, and then what we do is when you are going to choose a color, you just always try to choose the lowest color you can. Okay, and that means that if there's a register available, you pick the register. If there's no register available, you'll pick a stack location. One thing that's kind of cool about this is that just like you reuse registers when you've got different live variables, you can also sort of reuse stack locations And so that helps to minimize the amount of stack space that you need for your local variables based on liveness. Yeah.
The Sudoku is a 3x3 construction each unit, but well, does it have to be 3x3? If you go 4x4 for each component, then you get something similar to the 0 to 15 register.
Well, this whole board corresponds to like if you think about how many variables this board corresponds to, it's 1, 2, 3, 9 times, it's 81 variables, right?
Oh.
On this board,
Okay.
right? Because each tile is a variable. And then this is like trying to allocate 91 or 81 variables onto 9 registers.
So you can use 15 registers, those 15 registers with an expanded version of the
Right. Right. But now like Sudoku, the edges get determined just by the layout of the board, right? Whereas if you're coming from a program, your edges get determined by, the live ranges of your variables. And would typically be much more sparse than a Sudoku board, which makes things a bit easier.
Could you find that this the analogy helps students understand the algorithm?
Yeah.
Much faster way.
Yeah, because they sort of already know how to do it. So it turns out that this algorithm is it's a slightly more complex version of an algorithm that some people came up with for when your intermediate representation is in SSA form. You can use what's called a chordal graph coloring algorithm, which is super fast and optimal for chordal graphs. And so that gets used in some JITs, for example, in Java. And so this algorithm is just maybe slightly more sophisticated than that one, not much. Using sort of pure saturation.
What kind of time do production level compilers spend on solving this problem?
On register allocation?
Yes.
So, most of them, most of what I call the typical sort of static, ahead of time compilation compilers like GCC do graph coloring. They don't use this exact algorithm, but they do. These algorithms typically are n squared, the number of variables in your program. So the register allocator oftentimes is one of the more expensive. Most of your passes are just linear time, right? And then you hit register allocation, and that's n squared. And so Kent Dybvig used to say oh, who cares about how many passes you have? Because you're just going to do you're going to be n squared in your register allocator anyways. And so there's some truth to that. But at some point you do care about some of the constant factor, some of that linear time stuff.
I also think there's a fairly big gap between the register allocators that are described in the literature and what actual production compilers.
Yeah.
I sort of felt none of the graph coloring stuff quite scaled well enough, and there's a bunch of weird stuff that people do, and I know at Jason we were spending quite a lot of time trying to make the register allocator better, and it's just not.
Yeah. So
and it's a very big part of compilation.
Yeah.
Especially in topological files.
Right. So there's a kind of a spiel that I do in the lead up to this register allocation thing, which is that this is an example where we're doing a certain mathematical model of a problem, right? And in that step, we're abstracting away from lots of actual details about what's going on, and losing out on a lot of information. And so in many ways, just the pure graph coloring thing is not giving you the best results. And so what are things that you would want to consider? And I have some pointers into the literature, but you might want to consider how often is a variable actually used at runtime? It's because let's say you got one variable that's in an inner loop and another variable that's not. Obviously, you want to prioritize that one in the inner loop for getting a register. And if you're going to spill one, maybe spill the other one, right? And so, that's a thing that a production quality compiler absolutely would want to do. It would want to sort of do a static analysis that guesses, like predicts how much usage each variable is going to get. Or you might even want to do runtime profiling. People have done that where they do runtime profiling to sort of gather statistics on which variables are used more. Another thing that's important is, what if you have a variable that's used in an inner loop, and then much later on, used not in a loop? Okay, and maybe you want to prioritize it in one part of its range, but in another part of its range, you'd rather just spill it because it doesn't matter. So how could you make different decisions about the same variable? And so like this simple algorithm that we learned here doesn't allow you to do that. But there is pointers into the literature in this chapter where it says, oh, there's a thing called live range splitting, where you can take one variable and essentially split it into two different variables, and then make separate decisions. And so, kind of to answer your question, Aaron, is that it's like this is the tip of the iceberg, and then then you really get to sort of like, oh, and then this is where you can branch out into the literature and do next steps. It's actually we've got 4 minutes left, so I'm not going to do any more material per se, but if happy to answer some more questions in our remaining time.
I choose Python and records as well, right? The other one.
Yeah, so part of that's historical. So this is a good chance for me to talk about the history. So I haven't had a chance to talk about that yet. So there's been a compiler course at Indiana University since like, I want to say the 70s or something like that. Okay, Dan Friedman was teaching it, and then his students, Kent Dybvig, were teaching it. And Kent Dybvig was building, early on, they came up with this idea of NanoPass and of having all these interpreters for your intermediate languages so you could test everything. So that goes way back to those guys. And Dybvig was also, building Shea scheme and really wanting to make that fast. And so a lot of the how the compiler works in this here is based on those ideas from Shea scheme. And I took his course in like the early 2000s from Dybvig. And so all that work was in Scheme. Yeah, it was in Scheme, which is of course a predecessor to Racket. We switched to Racket in the last maybe 8 years or so, just because like Racket just has such good tooling over the schemes. So, and it's actually interesting that Shea scheme is now inside of Racket. Like Racket runs on Shea scheme. So that's even sort of more why like the techniques in this book are kind of fun, because you get to be like, oh, this is what's going on under the hood in Racket now. So that's why Racket. And we also teach Racket to our freshmen at IU. It's like our teaching language. So that's why that. Python. So when I finished my PhD at IU, I went on to teach at Colorado, at the University of Boulder, or University of Colorado Boulder. And this notion of doing incremental stuff had just, the idea for that was another grad student at IU that was co-temporal with me. Okay. And so when I started teaching compilers at Boulder, I was like, oh, I'm going to do incremental. But at Boulder, none of the students had ever seen Scheme or Racket. So that was like a non-starter. There's no way I was going to teach the compiler course in Racket or Scheme, because it's a programming intensive course. They got to do some language that they know. Right. And a lot of the students knew Python. And I also knew that I could sort of like, in some sense, de-sugar Python into a Racket or Scheme-like IR, and then really do like the Scheme compiler course, just with like this thin veneer on the front that sort of handles the sort of the differences with Python. And so, so I taught it in Python for many years out of Colorado, and then 7 years later, I moved back to IU and started teaching it again at Racket, and then decided, oh, it's finally stabilized after a while. And I'm like, okay, time to do textbook. And then so it was a natural choice then to do those two languages.
Do you have any feel for like what's different pedagogically between the two versions? I mean, now talking for a while.
I feel like there's not that big a difference nowadays. Like math, you got match in both languages. It's funny, my code is very similar. Like I use classes in OO in both languages for the same purpose of, getting those interpreters to sort of be extensible and stack up.
The Racket ones are all shorter as far as.
Yes. The syntax is more succinct. So they don't pedagogically.
Do you use typed or untyped brackets?
My code is in untyped Racket, but you notice that we're actually the input languages are typed Racket. So like the syntax for all the type annotations and stuff like that, that's in our programs that we're compiling, those are all actual typed Racket. Like you could take all those programs and run them in typed Racket. Get the
But you can include like the typing from the numeric tower.
Yeah, we do not do the numeric tower, but yeah. So that's yeah. So it really, we scratched the surface. This is meant to like really give you just kind of an overview. But it does hit a lot of the things that like, oh, higher level languages. These are, garbage collection, closures. These are all sort of higher level language features that a lot of compiler courses out there sort of shortchange, in my opinion. So that's kind of something that's about IU. And a lot of it's that we get rid of, because we get rid of parsing. We have space for that. Trade-off. I know there's a lot of the older compiler, experts that, kind of are like, oh, how could you possibly get rid of parsing?
It depends what you think your compiler's course is for. I feel like the thing you're most likely to write yourself out working somewhere is a parser.
Okay. Yeah.
But if the point of the compiler's course is to understand the foundations, I feel like the parser is the least interesting part, and the rest of it gives much more insight.
Yeah.
And I'm much more interested in the latter.
Right. I guess one good thing is that there are a ton of compiler books out there that do parsing.
Right.
And so I would be like, great, go get one of those. And if you want that. Yeah, if you want to know about the rest of it, then this gives you a nice overview. All right, we are now a little bit over time, so I'll stop. And it has been an absolute pleasure getting you fielding your questions today. Thanks.
Thank you. Most interesting.
I'm going to see if I get it. This is for computational geometry.
Past life, I did a tiny bit of computation.
Yeah.
Because I was doing graph algorithm stuff. They have that kind of a little bit of overlap there.
Yeah.
All right. This was my first time doing the live coding part of it. Was that fun to see, or what did you? how did you
Yeah.
think of that?
Yeah, it really shows the, I guess, how you actually build compilers in real life.
Mhm.
The debugging process is valuable as well.
Yeah, okay, cool.
Yeah, you give, this is a different way from how you give lectures.
Maybe I should try some of that in class too. In lecture, I sort of intentionally try to leave it more up to students to discover
Yeah,
how to do the coding.
yeah, it's just like the book, all of the important parts are hidden in the exercises.
Yeah. So there's sort of a balance. So this time I'm sort of giving more away, right?
Yes.
But yeah, there's sort of a balance there, and you know, actually, I'm almost wondering if maybe the right balance. I know some students struggle, especially this first couple of weeks, and so I think maybe I should do this like at the beginning, like in the first couple of weeks of the course, and then sort of scale back on how much live coding I do to let them figure it out.
But in class, because you need both consider the racket users and Python users, like you can just give Python code.
Yeah.
Yeah, you don't need to consider the other side.
Right, yeah. Oh, that's interesting.
Yeah, one trouble I have with programming courses is that the workflow for completing an assignment and your debugging process helps a lot with that.
Just to see, like, oh, that's the workflow.
Yes.
Yeah, okay, cool. Good, that's really good feedback.
This is pretty good for my first tutorial on compilers. Yeah. My impression is that so you take the source code and you just keep on shaping it into something you can pass to a compiler like x86.
Yeah. Yeah, that's right. And you keep just trying to get it low, abstractions lower and lower.
Yeah, and it's more like an art rather than a science.
Yeah, I think there's some truth to that.
Yeah, thank you.
We will need to stay out tomorrow. Okay, let's see you next week.
Yes.
How are you?
It's been a while.
Yeah. It looked like a nice active tutorial session.
I tried something totally different, but I didn't work with it, yeah.
Yeah.
And I